Deep in a laboratory beneath Switzerland, scientists trapped 100 atoms of antihelium for 3 millionths of a second before they vanished. This substance costs more than $60 trillion per gram. It annihilates on contact with anything. We are about to explore the rarest materials in existence, from elements that self-destruct through heat, to stars made of quarks that could convert your body into strange matter instantly, to black holes smaller than atoms that explode with the power of nuclear bombs. If you enjoy discovering what hides in the darkest corners of reality, prepare yourselves. We begin. Every particle you see has an evil twin lurking in physics equations. For every electron spinning in your body, there exists an opposite version with reverse charge. Scientists call this antimatter. When physicists first predicted antimatter in 1928, they thought mathematics had gone mad. The equations showed something impossible: particles with identical mass, yet opposite electric properties. 3 years later, cosmic rays proved the theory correct. Antimatter behaves like a photograph negative of reality. Where normal matter has negative electrons, antimatter contains positive ones called positrons. Where atoms have positive protons at their core, antiatoms contain negative antiprotons. The masses stay identical, only the charges flip. Here comes the terrifying part. Touch antimatter to normal matter and both explode instantly. The collision converts their entire mass directly into pure energy, following Einstein's famous equation. No chemical reaction comes close to this efficiency. Nuclear bombs release less than 1% of their fuel as energy. Antimatter converts 100%. Picture holding 1 gram of antimatter. Scientists confirmed this would release energy equal to 43,000 tons of explosives. The blast from 2 atomic bombs. From something weighing less than a sugar packet. Nature produces tiny amounts through specific processes. Lightning storms create positrons above thunderclouds. The belts of radiation around Earth trap small quantities of antiprotons. High-energy collisions in deep space generate antimatter particles constantly. Yet something happened early in cosmic history that remains unexplained. Theory suggests the Big Bang created equal amounts of matter and antimatter. Both should have annihilated completely, leaving only energy. Instead, a tiny imbalance occurred. For every billion antimatter particles, there existed 1,000,000,001 matter particles. That single extra particle in every billion became everything we see today. The missing antimatter ranks among science's deepest mysteries. Where did it go? Why did matter win? Some unknown process during the first second of existence tipped the scales. Physicists call this the baryon asymmetry problem. Today, antimatter exists as the rarest substance scientists can study. The largest particle accelerator on Earth produces about 1/1000,000th of a gram per year. Creating just 1 gram would require running that machine continuously for 1 billion years. Storage presents another nightmare. Antimatter cannot touch any container wall. Any contact means instant annihilation. Scientists use powerful magnetic fields to levitate individual antiparticles in perfect vacuum chambers. Even then, storage times measure in minutes before the particles escape and explode. What happens when researchers finally captured enough antimatter to test directly makes the impossible seem possible. In 2011, researchers at Europe's particle physics laboratory achieved something that should not exist. They created antiatoms of helium, not individual antiparticles, complete antiatoms with structure and stability. Normal helium has 2 protons and 2 neutrons at its center, surrounded by 2 electrons. The antihelium these scientists built contained 2 antiprotons and 2 antineutrons, orbited by 2 positrons. A perfect mirror image of regular helium. The difficulty of this accomplishment defies imagination. First, you need a particle accelerator 17 miles around, running at nearly maximum power. Second, you must smash particles together at speeds approaching light velocity. Third, You must identify the few antihelium atoms among billions of other collision products. Fourth, you must trap them before they touch anything and vanish. The team succeeded in creating exactly 9 complete antihelium atoms. They existed for 30 billionths of a second before hitting detector walls and exploding into radiation. Think about that number, 9 atoms. The entire annual antimatter production of the most advanced scientific facility on Earth could fit inside a space smaller than a single bacterium. These 9 atoms represented years of work by hundreds of scientists operating equipment that cost billions of dollars. Yet this confirmed something extraordinary. Antimatter follows the same physical laws as normal matter. The antihelium atoms showed identical spectral signatures to regular helium. Their structure matched perfectly. This means antimatter could theoretically form anti-stars, anti-planets, even anti-galaxies somewhere in space. Astronomers search for such regions constantly. If antimatter galaxies existed, they would emit unique signatures. The boundary between matter and antimatter regions would produce constant gamma-ray explosions as particles from each side mixed and annihilated. Satellites scan the cosmos for this telltale radiation pattern. So far, nothing confirmed. The entire observable universe appears built from normal matter. Any antimatter galaxies remain hidden beyond detection range, or they never formed at all. The cost of producing antimatter makes it simultaneously the most expensive and most worthless substance imaginable. Scientists estimate antihydrogen costs $62 trillion per gram, the entire economic output of 3 United States economies for 1 year. For 1 gram, creating antimatter requires pumping in exactly the same energy you get from annihilation. You cannot use it as fuel. You cannot weaponize it practically. The containment systems weigh thousands of times more than any antimatter they could hold. Some researchers suggest antimatter could power deep space missions someday. The perfect efficiency of matter-antimatter annihilation would enable spacecraft to reach incredible velocities. 100 grams could theoretically push a ship to 10% light speed. The practical problems remain unsolved. How do you store it safely during years-long missions? How do you control the annihilation rate precisely? How do you shield the crew from radiation? How do you afford producing it in the first place? Despite these obstacles, antihelium represents just the second rarest form of antimatter scientists have created. The rarest form exists in quantities that make 9 atoms seem abundant. The moment antimatter touches normal matter, physics enters its most violent mode. 2 particles meet. Both cease to exist. Energy erupts outward at light speed. This process operates fundamentally different from any chemical reaction or nuclear process we know. Burning gasoline breaks molecular bonds and releases energy stored there. Nuclear fission splits atoms and converts a fraction of mass to energy. Antimatter annihilation converts everything to energy. Scientists have measured this process precisely. 1 kilogram of antimatter meeting 1 kilogram of matter releases energy equivalent to 43 megatons of explosives, about 3,000 times more powerful than the bomb dropped on Hiroshima. From just 2 kilograms of material, the annihilation produces specific signatures. When an electron meets a positron, they spiral toward each other, accelerating to extreme velocities. At the moment of contact, both vanish and emit 2 gamma-ray photons flying away in opposite directions. Each photon carries exactly 511,000 electron volts of energy. This energy signature allows scientists to detect antimatter creation events. Any process generating positrons leaves this fingerprint in the gamma-ray spectrum. Thunderstorms produce detectable positron emissions. Certain radioactive materials emit positrons as they decay. Even medical scanners use this effect deliberately. Positron emission tomography machines inject patients with radioactive tracers that emit positrons. Those positrons travel tiny distances through tissue before meeting electrons and annihilating. The resulting gamma-ray pairs reveal metabolic activity inside organs and tumors. When heavier antimatter particles collide with their matter counterparts, the annihilation becomes more complex. Antiprotons meeting protons produce showers of other particles. Pions, kaons, and various mesons spray outward, carrying the energy away. These daughter particles themselves decay within microseconds, creating cascades of radiation. The total energy released follows Einstein's equation precisely: mass multiplied by the speed of light squared. Since light travels about 186,000 miles per second, squaring that number produces an enormous multiplier. Even tiny masses become huge energies. 1 gram of matter contains about 9 times 10 to the 13th joules of energy. That equals 21,000 tons of TNT equivalent. 2 grams annihilating would double it. 10 grams would release energy, matching the largest nuclear weapons ever tested. Nature demonstrates this power constantly on tiny scales. Cosmic rays slamming into atmospheric molecules at relativistic speeds create matter-antimatter pairs that immediately annihilate. The showers of particles produced cascade downward through the air. About 100 of these particles pass through your body every second. The largest antimatter reserves in our solar system exist in radiation belts trapped by Earth's magnetic field. Satellites have detected antiprotons circling our planet at altitudes of several hundred miles. These antiprotons likely originated from cosmic ray collisions and became trapped. Similar belts probably exist around Jupiter, Saturn, and other planets with strong magnetic fields. Scientists have captured and stored individual antiprotons for over 1 year in specialized magnetic traps. This represents the longest any antimatter has existed in human custody. The moment those magnetic fields fail, the antiprotons fly outward and strike the chamber walls. Each produces a tiny flash of energy as it vanishes forever. Even with perfect storage, antimatter faces another limitation: the vacuum itself. Scan the entire planet. Check every rock formation, every ocean bed, every mountain peak. Search all 6 million trillion pounds of Earth. You will find less than 1 ounce of a substance so rare scientists debate whether it even deserves study. Element 85 sits on the periodic table marked At for astatine. The name comes from Greek, meaning unstable. That label undersells the reality by a massive degree. Astatine atoms cannot exist for more than a few hours before self-destructing. The most stable version, astatine 210, survives 8 hours on average before splitting apart. Most forms last mere seconds. This rapid decay means any astatine present when Earth formed has long since vanished. The tiny amounts existing today form continuously through radioactive decay chains. When uranium and thorium atoms break down, they occasionally produce astatine as an intermediate step. That astatine then decays almost immediately into other elements. The process maintains roughly 25 grams, spread across the entire planet at any moment. Finding this distribution makes finding specific grains of sand on all Earth's beaches seem simple. One calculation estimated that the total landmass of North and South America combined, reaching 10 miles deep, contains about 1 trillion astatine 215 atoms at any instant. That amounts to about 3/10 billionths of a gram. Scientists cannot collect natural astatine samples. By the time you identified where an atom formed, it has already decayed. Every study of astatine requires artificial production in particle accelerators. Researchers bombard bismuth metal with alpha particles, creating astatine atoms one at a time. Even then, the quantities remain absurdly small. The total amount of astatine produced by all laboratories throughout history adds up to less than 1/10 millionth of a gram, about 500 nanograms. If you gathered every astatine atom ever created by humans into one place, it would be invisible even under powerful microscopes. Why does astatine decay so rapidly? The nucleus contains 85 protons crammed into a space smaller than an atom. that many positive charges repel each other with intense force. The strong nuclear force barely holds them together. Any tiny quantum fluctuation breaks the balance and the atom flies apart. Nobody has ever seen pure astatine in elemental form. Theory suggests it would appear as a dark, possibly metallic solid at room temperature. Scientists base this prediction on astatine's position below iodine on the periodic table. Halogens get darker as they increase in mass. Fluorine appears nearly colorless. Chlorine shows yellow-green. Bromine glows red-brown. Iodine displays dark gray-violet. Astatine should be darker still. The prediction remains untested because accumulating enough astatine to see creates an insurmountable problem. The intense radioactivity from even microscopic amounts would generate heat through particle emission. That heat would vaporize the sample instantly. Any visible quantity of astatine would literally boil itself into gas through its own radioactive decay. Some calculations estimate that assembling 1 microgram, 1/1,000,000th of a gram, would produce enough heat to immediately vaporize the sample and possibly damage surrounding equipment. The element earns the nickname "goodbye" for good reason. Despite existing in nearly unmeasurable quantities, astatine might become crucial for medicine. Certain isotopes emit alpha particles, high-energy radiation excellent at destroying cancer cells while causing minimal damage to surrounding healthy tissue. Researchers test astatine-211 attached to antibodies that target tumors. Early trials show promise. The radiation acts like a microscopic bomb delivered directly to cancer cells. The 8-hour half-life gives doctors enough time to prepare and administer treatments before the astatine decays away. The challenge remains producing and transporting enough astatine from accelerators to hospitals before it vanishes. Current methods create only tiny amounts that must be used within hours of production. What happens when astatine encounters certain conditions reveals why it earns its reputation as the most unstable natural element. Imagine holding a substance so radioactive it glows from its own energy. Now imagine that glow generating enough heat to melt the material instantly. Then imagine the molten material evaporating into gas before cooling. This describes astatine in bulk quantities that have never existed. Every astatine atom contains a nuclear time bomb. The 85 protons packed into its nucleus maintain an unstable balance. When that balance breaks, the atom ejects particles at tremendous speed. Those particles carry energy measured in millions of electron volts. In normal radioactive materials, individual decay events happen spread apart. One atom decays here, another decays there. The energy dissipates safely into surroundings. With short-lived elements like astatine concentrated together, every atom decays within hours. The energy density becomes enormous. Scientists calculated what would happen to a visible sample of astatine-210. Start with 1 milligram, roughly the size of a small grain of sand. That quantity contains about 3 trillion atoms. All 80 billion atoms decay within 24 hours on average. Each decay releases about 6 million electron volts. Convert those numbers into heat energy. The sample would produce over 100 watts of power continuously, about the same as a bright light bulb. From a grain-sized piece of material, the temperature would spike to thousands of degrees within seconds. Solid astatine would melt. Liquid astatine would boil. Gaseous astatine would glow white-hot in the air, all within moments of formation. Any container would need active cooling systems to prevent the astatine from destroying itself and everything nearby. The situation gets worse as you increase quantity. Double the astatine and you double the power output. 10 times more material generates 10 times more heat. At some point, no cooling system could compensate. The sample would undergo runaway heating until complete vaporization. This self-destruction property makes astatine essentially impossible to study through conventional chemistry. Traditional methods require weighing samples, dissolving them, precipitating them, analyzing their crystal structures. Every technique assumes you can handle bulk material. With astatine, bulk material means working with billions of atoms instead of millions. Quantities measured in picograms, trillionths of a gram. At these scales, individual atoms matter. Statistical averaging breaks down. Contamination from single molecules skews results. Researchers have developed workarounds using tracer techniques. They mix astatine atoms with much larger quantities of similar elements, like iodine. The astatine follows the iodine through chemical reactions. Radiation detectors track where the astatine goes. This allows studying astatine's chemical behavior without ever having pure samples. Results show astatine behaves unlike other halogens in surprising ways. It displays some metallic properties. It forms certain compounds that other halogens cannot. It appears to exist on the boundary between metals and non-metals on the periodic table. Theoretical calculations fill gaps in experimental knowledge. Supercomputers simulate astatine atoms and predict their properties. These predictions must rely on quantum mechanics and electromagnetic theory because real experiments remain impossible. One calculation addressed a basic question: what would solid astatine's crystal structure look like? The model suggested astatine would form diatomic molecules like iodine, with pairs of atoms bonding together. These pairs would then arrange into crystalline lattices. The predicted structure shows mixed metallic and covalent bonding. Another calculation predicted astatine's electron affinity, the energy released when an atom gains an electron. This measurement required bringing astatine atoms to a specialized facility and blasting them with carefully tuned lasers. The result matched theoretical predictions closely. Perhaps the strangest property involves astatine's practical applications. Despite its rarity, medical researchers cannot obtain enough astatine to study its chemistry directly. Yet they successfully use it to treat certain cancers. The treatments work because doctors need only billions of atoms per patient, not grams. Those billion atoms cost roughly $30,000 to produce. Treatment-grade astatine-211 exists for about 8 hours after creation. Hospitals must coordinate with nuclear facilities to receive shipments and administer treatments before decay renders the material useless. But astatine represents only the rarest naturally occurring element. Artificial elements achieve even greater rarity. Look at the periodic table. Count the elements from number 1 through number 94. Every single one appears naturally on Earth, except one. Element 61 stands empty. A gap in nature's collection. Scientists named the missing element promethium after the Greek Titan who stole fire from the gods. The name fits. Promethium's radioactivity makes it a fire that cannot be contained. When researchers first assembled the periodic table, they noticed something wrong. Between elements 60 and 62 sat a predicted element that nobody could find. Neodymium exists naturally. Samarium exists naturally. Whatever sat between them remained absent. The reason eluded scientists for decades. Element 61 should exist. Its position suggested properties similar to neighboring rare earth metals. Those metals appear abundantly in minerals worldwide. Yet promethium never showed up in any sample. Multiple researchers claimed discovery between 1920 and 1940. Each claim proved false upon investigation. The supposed promethium signatures turned out to be other elements or experimental errors. The mystery deepened. Finally, in 1945, scientists at Oak Ridge National Laboratory created promethium artificially by bombarding uranium with neutrons in a nuclear reactor. The process produced promethium as a fission product. They isolated a sample and confirmed its properties matched predictions. The explanation for promethium's absence became clear. All promethium isotopes are radioactive with relatively short half-lives. The longest-lived version, promethium-145, survives about 18 years on average. Any promethium present when Earth formed decayed away billions of years ago. Today, promethium exists only through artificial production or as an extremely rare byproduct of uranium decay. Natural uranium occasionally splits spontaneously through fission. This produces tiny amounts of promethium that decay within years. Scientists estimate perhaps 500 grams exist naturally across the entire planet at any moment. Even this tiny amount dwarfs what humans have produced. Total artificial promethium production since discovery amounts to less than 1 kilogram. The element serves few practical purposes. Some satellite batteries used promethium oxide to generate electricity through radioactive decay. That application has largely been abandoned. Promethium glows in the dark, not through fluorescence or phosphorescence. The radioactive decay itself excites electrons in surrounding material, making it emit blue-green light. A sample of promethium salt produces visible light continuously without any external energy source. This property led to early applications in luminous paint for watch dials and instrument panels. Safety concerns ended this use. The radiation posed health risks to workers handling the paint and to people wearing the devices. The rarity of promethium creates strange situations in chemistry. Students learn about all elements through hands-on experiments and visual demonstrations. Promethium remains theoretical for nearly everyone. Even professional chemists rarely encounter it. Most periodic tables show an empty square or a note saying radioactive, artificially created. Obtaining promethium for research requires special permits and access to nuclear facilities. The material arrives in microscopic quantities sealed in protective containers. Experiments must be designed to work with nanogram amounts. Standard chemical techniques fail at these scales. One unusual fact about promethium involves its oxide form. When chemists tried creating promethium oxide for battery applications, they discovered the material displayed unusual optical properties. It absorbed and emitted light at specific wavelengths. This led to proposals for using promethium in specialized lasers. The proposals never advanced beyond theory. Producing enough promethium oxide for a laser would cost millions of dollars and require years of continuous reactor operations. The resulting laser would have no advantages over conventional designs. The entire concept remained an expensive thought experiment. Natural promethium production on Earth pales compared to stellar environments. Inside dying stars, promethium forms continuously through nuclear processes. The element exists briefly before decaying into samarium. Analyzing starlight sometimes reveals promethium's spectral lines, providing evidence of active nuclear reactions in stellar atmospheres. This connection between Earth's rarest elements and stellar processes hints at deeper connections. Everything heavier than hydrogen formed inside stars or during stellar explosions. The presence or absence of specific elements on Earth reveals our planet's nuclear heritage. Some proposed explanations for promethium's rarity suggest testing them might reveal fundamental physics. What if promethium isotopes exist with longer half-lives under certain conditions? What if neutron-rich environments could produce stable promethium? These questions lead to even stranger possibilities. Could exotic matter exist with properties that make common elements seem abundant? Take a teaspoon, fill it with star material, place it on a scale. The needle would read 4 billion tons. This weight would crush through the scale, through the floor, through the Earth's crust, and sink toward the planet's core. Neutron stars represent matter compressed beyond normal limits. When massive stars exhaust their fuel, they explode in supernovas. The cores that remain collapse under their own gravity. Atoms get crushed into oblivion. Electrons get forced into protons, creating neutrons. Those neutrons pack together so tightly that a city-sized sphere contains more mass than our entire home star. Picture compressing all of humanity, 8 billion people, into a space the size of a sugar cube. That approaches neutron star density. Every cubic inch contains the mass of Mount Everest. The pressure inside these objects defies description. At the surface, gravity pulls with 100 billion times Earth's force. Falling from a height of 1 inch would accelerate an object to thousands of miles per hour before impact. Mountains on neutron stars cannot rise more than a few millimeters before the gravity flattens them. The surface itself displays bizarre properties. Scientists believe it forms a crystalline lattice of iron nuclei frozen into the hardest material in the universe. This crust measures perhaps 1 mile thick and possesses strength trillions of times greater than steel. yet it floats on something stranger beneath. Below the crust exists an ocean of superfluid neutrons. These neutrons flow without friction, without viscosity, without any resistance. They form a quantum liquid that behaves unlike any normal fluid. Waves in this ocean would propagate forever, never damping or dissipating. Diving deeper reveals more extreme conditions. Neutrons pack so tightly they begin touching. Remember that neutrons themselves have internal structure. Each contains 3 quarks held together by the strong nuclear force. Under neutron star pressures, those quarks might break free from their confinement. This possibility leads to one of the strangest ideas in astrophysics. If pressures grow high enough to dissolve neutrons completely, the quarks might rearrange into different patterns. Instead of 3 quarks per particle, you might get free-floating quarks forming a quark liquid. Theory suggests this transition happens at about twice normal nuclear density. Many neutron stars likely reach these conditions at their cores. What exists there remains uncertain. Ordinary matter cannot exist. Neutron matter probably cannot exist. Something else must fill that space. Observing neutron stars provides clues about their interiors. When neutron stars spin, they emit beams of radiation like cosmic lighthouses. These pulsars flash with incredible precision. Some keep time more accurately than atomic clocks. The spin rates, gravitational effects, and cooling patterns all reveal information about internal structure. Recent observations detected neutron stars more massive than scientists predicted. The heaviest confirmed examples contain about twice the mass of our home star compressed into a sphere 12 miles across. Theory suggested such massive neutron stars should collapse into black holes. Their existence pushes models to extreme limits. These massive neutron stars might contain exotic forms of matter, stabilizing them against collapse. Perhaps strange quarks appear in their cores. Perhaps even stranger particles emerge under such extreme compression. When 2 neutron stars collide, they create the most violent events in the cosmos, short of supernovas. The collision melts both stars, sending shock waves through the neutron fluid. Material gets ejected at substantial fractions of light speed. The merger might form a more massive neutron star or collapse directly into a black hole. Gravitational wave detectors have captured signals from multiple neutron star mergers. The waves carry information encoded in their pattern. By analyzing the signals, scientists can estimate how stiff or soft neutron star matter behaves. Stiff matter resists compression and allows larger neutron stars. Soft matter compresses easily and limits maximum masses. Current data suggests neutron star matter behaves stiffer than many models predicted. This implies the strong nuclear force remains powerful even at extreme densities. The quarks inside neutrons might resist dissolving into free quarks longer than expected. These findings connect directly to one of physics's deepest mysteries. What happens to matter under ultimate compression? Does it resist indefinitely? Does it undergo phase transitions into exotic states? Does it eventually surrender to gravity and collapse into a singularity? The answer might involve particles that should not exist according to standard theory. Everything around you is built from 2 types of quarks, up quarks and down quarks. These combine in threes to form protons and neutrons. 2 ups plus 1 down makes a proton. 2 downs plus 1 up makes a neutron. These combinations generate every atom in existence. Or so it seems on the surface. Nature actually provides 6 varieties of quarks. Up and down represent only the lightest pair. 4 heavier flavors exist with peculiar names: strange, charm, top, and bottom. These exotic quarks appear in high-energy physics experiments, then decay almost instantly into their lighter cousins. Strange quarks earned their name from their peculiar behavior when first discovered. Particles containing strange quarks lived longer than expected and exhibited unusual properties. Physicists literally found them strange. The name stuck. A strange quark weighs about 30 times more than an up or down quark. This extra mass makes strange quarks unstable in normal conditions. They decay through the weak nuclear force, transforming into lighter quarks within fractions of a second. Strange particles never survive long enough to incorporate into regular matter. Inside particle colliders, scientists create strange quarks constantly. Smash protons together hard enough and heavy quarks materialize from the energy. These heavy quarks immediately begin forming short-lived particles called strange mesons or strange baryons. Within billionths of a second, the strange quarks decay and the particles vanish. This rapid decay made strange quarks seem irrelevant to large-scale structures. Yes, they exist briefly in laboratories. Yes, cosmic rays occasionally produce them when striking the atmosphere, but they disappear too quickly to matter for planets, stars, or galaxies. Standard physics assumes strange quarks play no role in bulk matter. Then theorists asked a simple question: what if strange quarks could become stable under extreme pressure? The idea seems counterintuitive. Strange quarks are heavier than up and down quarks. Heavier particles typically require more energy to create and maintain. They should be less stable, not more stable. Yet the mathematics of quark interactions suggested something surprising. At normal densities, strange quarks immediately decay. The weak force converts them to lighter quarks and releases energy. This happens because strange quarks exist individually or in unstable combinations. But compress quarks together to extreme densities and the rules change. When quarks pack tightly enough, they enter a regime where quantum effects dominate. Quarks are fermions, particles that obey the Pauli exclusion principle. This principle states that no two identical fermions can occupy the same quantum state simultaneously. For quarks, this means only so many up quarks or down quarks can exist at each energy level. Fill up all the low energy states with up and down quarks, and adding more quarks forces some to occupy high energy states. At some point, having a strange quark in a low energy state costs less energy than having a down quark in a high energy state. The strange quark becomes favorable. This transition might occur at densities around twice normal nuclear density. Neutron star cores likely reach these densities. Instead of pure neutrons, the cores might contain free-floating quarks in a mixture of up, down, and strange varieties. Theory predicts this strange quark mixture could be stable or even more stable than regular nuclear matter. If true, strange quarks would not decay under these conditions. They would persist indefinitely, forming a new phase of matter called strange quark matter. The implications seem bizarre at first. A substance containing roughly equal numbers of up, down, and strange quarks would have lower energy per particle than normal nuclei. It would represent matter in its true ground state. Everything we consider normal would actually be metastable, existing temporarily because converting to strange matter requires extreme triggering conditions. Computer simulations of quark behavior at extreme densities support this possibility. The strong nuclear force that binds quarks together behaves differently when many quarks crowd into small volumes. Color superconductivity might emerge, allowing strange quarks to form Cooper pairs similar to superconducting electrons. These exotic quantum effects could lock strange quarks into stable configurations. The resulting matter would possess unprecedented density and strength. It would resist further compression. It might form self-bound objects held together by quark interactions rather than gravity. If such objects exist, they would inhabit a narrow range between neutron stars and black holes. Too light and gravity cannot compress matter enough to create strange quarks. Too heavy and collapse to a black hole becomes inevitable. The sweet spot might span masses from about twice our home star up to 3 times that mass. Some observations hint at candidates in this mass range. A few neutron stars appear unusually compact for their mass. Others cool faster than standard models predict. These anomalies might indicate strange quark cores forming inside, but these cores would remain hidden inside neutron stars. The real test involves a much more radical prediction. What if strange matter can exist as independent objects? Imagine a droplet of liquid so dense a marble-sized sphere weighs more than Mount Everest. Now imagine this liquid can convert any normal matter it touches into more of itself. Finally, imagine that billions of these droplets might drift through space undetected. Scientists call these hypothetical objects strangelets. They represent fragments of strange quark matter, small enough to qualify as particles, yet large enough to contain millions or billions of quarks. Their size could range from atomic nuclei up to grains of sand. Larger fragments are called strange stars. Strangelets should form whenever strange matter gets broken apart violently. When neutron stars collide, the impact might create cores of strange matter that fragment during the explosion. Each fragment becomes an independent strangelet shooting into space. When strange stars form, surface instabilities might eject strangelets through some cosmic equivalent of evaporation. Early theoretical models suggested strangelets should evaporate quickly. Small fragments have large surface areas relative to their volume. Surface effects should destabilize the quark arrangement and cause decay back to normal matter. For decades, physicists assumed strangelets could not persist long enough to matter. Recent calculations paint a different picture. Surface tension at the boundary between strange matter and vacuum might be much lower than originally estimated. Low surface tension allows strangelets to resist fragmentation. They might remain stable across a wide range of sizes. If stable strangelets exist, their properties would be extraordinary. Unlike normal matter held together by electromagnetic forces, strangelets would bind through the strong nuclear force acting directly between quarks. This creates objects far more robust than regular nuclei. A strangelet the size of a virus might weigh as much as a small mountain. Its surface would not consist of atoms or molecules. Instead, a thin layer of electrons would surround the bare quark liquid, neutralizing its electric charge. From a distance, a strangelet would appear as an unusually heavy isotope of some element, with mass numbers far exceeding anything found naturally. Detecting strangelets presents enormous challenges. If they move through space, they would resemble cosmic rays, but with extremely high mass to charge ratios. Magnetic fields barely deflect them. Most cosmic ray detectors would miss them entirely. Underground neutrino detectors might occasionally register a strangelet passing through rock, but the signal would be ambiguous. Some researchers searched for strangelets incorporated into Earth's matter. After billions of years, occasional strangelets drifting through the solar system should collide with our planet. If strangelets are truly stable, they would survive the impact and sink into the Earth. Eventually, they would settle near the core, the deepest gravitational low point. Searching for heavy anomalous isotopes in terrestrial samples should reveal strangelets if present. Scientists have analyzed rocks, meteorites, and ocean sediments. No confirmed strangelets have appeared. Either they are extraordinarily rare, or they do not exist, or they possess properties that make detection even harder than expected. One controversial question involves whether strangelets might catalyze conversion of ordinary matter. Some models predict that a strangelet touching normal atomic nuclei could trigger a chain reaction. Quarks from the nucleus might reconfigure into the strange matter arrangement. The newly converted material would add to the strangelet's mass. The process would repeat, converting everything it touches. This scenario inspired concerns about particle accelerator experiments. When heavy ions collide at relativistic speeds, conditions briefly resemble the early universe or neutron star interiors. Could such collisions create strangelets? Could those strangelets convert Earth into strange matter? Detailed analysis showed these fears were unfounded. Natural cosmic rays strike Earth's atmosphere with far more energy than any accelerator produces. If strangelet creation and conversion were possible, it would have happened billions of times already from cosmic ray impacts. Earth's continued existence demonstrates either strangelets cannot form easily, or they cannot catalyze conversion, or both. The Large Hadron Collider achieved energies approaching those needed to create strange matter. Experiments searched specifically for signs of strangelet production. Detectors looked for particles with unusual mass-to-charge ratios, unexpected stability, and other signatures. Years of operation revealed nothing convincing. This null result limits, but does not eliminate, the strangelet hypothesis. Accelerator collisions create hot, sparse quark matter that cools rapidly. Strange matter might require sustained high density and pressure to stabilize. Brief collisions might not provide sufficient time for strange quarks to organize properly. Neutron-star mergers create dramatically different conditions. Colliding neutron stars produce huge volumes of ultra-dense matter maintained for seconds. Temperature and pressure remain extreme during the entire event. If strange matter forms anywhere, neutron-star collisions offer the best opportunity. Gravitational wave detectors captured signals from several neutron-star mergers. Analysis revealed details about the collision dynamics. The mergers created hot, massive objects that persisted briefly before either forming more massive neutron stars or collapsing into black holes. In some cases, the final fate remains unclear. One intriguing event involved two moderately massive neutron stars merging. The mass of the combined object exceeded the theoretical limit for pure neutron matter. Standard models predict immediate collapse to a black hole. Yet the gravitational wave signal suggested a compact object survived for at least several seconds before the signal ended. Could the merger have created strange matter? Could the resulting object be a strange star rather than a neutron star? Could fragments have been ejected during the collision, sending strangelets speeding through interstellar space? These questions remain open. What happens when strange quarks dominate an entire stellar object reveals even more extreme possibilities. One theoretical possibility haunts physicists studying strange matter. What if it represents the true ground state of all matter? What if everything around you exists in an unstable form that could transform catastrophically? Normal matter appears stable because atoms are stable. Protons and neutrons bind into nuclei. Electrons orbit those nuclei. The arrangement lasts indefinitely under typical conditions. We trust this stability implicitly. Every technology, every biological process, every structure depends on atoms remaining atoms. Strange quark matter challenges this assumption. Theory suggests matter composed of equal parts, up, down, and strange quarks might have lower energy than matter composed of only up and down quarks. Lower energy means greater stability. If this hypothesis proves correct, then regular atomic nuclei would actually be metastable states, waiting to decay into their true ground form. The barrier preventing this decay would be enormous. Converting ordinary matter into strange matter requires completely rearranging its quark content. Nuclei must dissolve. Individual quarks must reconfigure. Strange quarks must materialize from available energy. This sequence demands conditions far beyond anything on Earth or inside normal stars. But introduce a seed of strange matter and the situation changes. That seed contains quarks already in the stable configuration. Ordinary quarks touching it might join the arrangement. The energy released from dropping into a lower energy state could help convert nearby quarks. A chain reaction becomes possible. Models of this conversion process predict it would propagate at close to light speed. Strange matter touches a nucleus. Quarks from the nucleus reconfigure within microseconds. The released energy triggers conversion in adjacent nuclei. A wave of transformation spreads outward in all directions. If started on Earth, such a wave would convert the entire planet to strange matter in about 1/10 of a second. The process would release energy equivalent to countless nuclear bombs, but spread across the whole planetary volume. From outside, observers would see Earth's mass remain constant while its radius shrinks to about 100 meters. The planet would become a strange matter sphere, the size of a football field. This apocalyptic scenario depends critically on whether strange matter truly is more stable than nuclear matter. The answer involves calculations at the frontier of quantum chromodynamics, the theory describing quark interactions. These calculations remain uncertain because the strong force behaves in complex ways at relevant energy scales. Current best estimates suggest strange matter might be slightly more stable than nuclear matter, or possibly slightly less stable. The energy difference appears small enough that uncertainties in calculation exceed the gap. Until better theoretical tools or experimental tests resolve this question, the true stability of strange matter remains unknown. Most physicists lean towards strange matter being unstable or only marginally stable. Several arguments support this view. First, neutron stars exist in large numbers. If strange matter were much more stable, we would expect most neutron stars to contain strange matter cores. Observational evidence suggests pure neutron matter remains the dominant component in most cases. Second, high-energy collisions in particle accelerators and cosmic rays have not produced persistent strange matter. Experimenters actively search for long-lived strange particles. None have appeared in convincing quantities. If strange matter formation were easy, these experiments should have detected it. Third, the observed abundance of ordinary matter throughout the universe suggests it maintains genuine stability. Matter has existed for nearly 14 billion years without spontaneous conversion to any exotic alternative. This longevity implies deep stability rather than metastability. However, these arguments do not prove strange matter cannot exist under specialized conditions. Neutron star cores might contain stable strange quark matter isolated inside layers of neutron matter. Particle collider conditions might differ too much from neutron star interiors to nucleate strange matter. The universe's matter composition reflects the Big Bang's outputs, which might not have included strange matter seeds. Testing strange matter stability experimentally proves difficult. Creating even small amounts requires achieving neutron star core densities in controlled settings. Current accelerators fall short of this goal. Future facilities might reach the necessary conditions, but construction would take decades and cost billions of dollars. Alternative approaches involve observational astronomy. Strange stars, if they exist, should display unique signatures, distinguishing them from neutron stars. Their cooling rates might differ. Their maximum spin rates might be faster or slower. Their response to accretion of normal matter might produce distinctive radiation patterns. Some candidates have emerged. A few compact objects show properties that fit strange star models better than neutron star models. These objects appear too small for their mass, or cool too quickly, or emit unexplained radiation. However, alternative explanations involving exotic neutron star physics can also account for the observations. One compelling piece of evidence would be detecting a strange star's surface directly. Unlike neutron stars with crusts of atomic nuclei, strange stars should have bare quark surfaces covered only by thin electron atmospheres. The surface properties would differ dramatically. Radiation from such surfaces would show characteristic spectra impossible to fake. X-ray telescopes search for these signatures. Several missions have observed promising candidates without finding definitive proof. The signals remain ambiguous. Improved instruments scheduled for launch in coming years might resolve the question. If strange stars exist, their presence raises profound questions. How common are they? How do they form? Can they collide with neutron stars and trigger conversion? Could a strange star lurk undetected in our cosmic neighborhood? The search for answers leads to objects operating under even more bizarre physical rules. Take a neutron star, compress it further, force the neutrons closer together until they overlap and dissolve. The quarks inside break free from their confinement. What remains is a quark star, an object so dense that describing it requires inventing new vocabulary. Normal matter has density measured in grams per cubic centimeter. Water rates 1, rock rates about 3. The densest normal materials reach perhaps 20. Nuclear matter inside neutron stars reaches 300 million trillion. A matchbox full would weigh more than Mount Everest. Quark stars exceed even this extreme density. Neutrons themselves get crushed out of existence. The quarks they contain merge into a continuous fluid. This quark matter achieves densities approaching 1 billion trillion times denser than water. A sugar cube full would outweigh every mountain on Earth combined. At these densities, the concept of individual particles breaks down. Quarks still exist as fundamental entities, but their wave functions overlap extensively. Each quark interacts simultaneously with countless neighbors through the strong nuclear force. The system behaves as a quantum liquid with properties unlike anything in normal experience. Standard fluids flow through the motion of molecules sliding past each other. Quark liquids flow through collective quantum excitations. Viscosity becomes a quantum mechanical concept. Temperature relates to the Fermi energy of the quark sea. Pressure connects to the quark-quark interactions mediated by gluons. The quarks inside these stars might enter special states called color superconductivity. Just as electrons can form Cooper pairs and flow without resistance in superconductors, quarks can pair up in specific combinations that eliminate energy dissipation. The entire quark liquid might flow without any internal friction whatsoever. These color superconducting phases have exotic names: color flavor locked matter, two-flavor superconductor, crystalline color superconductor. Each represents a different pattern of quark pairing and behavior. Which phase actually occurs depends on density, temperature, and the number of quark flavors present. Inside the quark star core, conditions might allow all three light quark flavors, up, down, and strange, to coexist in equal numbers. This three-flavor balance creates the color flavor locked phase, predicted to be the ground state of dense quark matter. In this phase, quarks pair across both color charge and flavor, creating a highly symmetric and stable configuration. The transition from neutron matter to quark matter should happen sharply at a critical density. Below this threshold, quarks remain confined inside neutrons. Above it, confinement breaks and quarks roam freely. The transition might occur through a phase change, similar to water freezing or boiling. Some models predict a mixed phase where neutron matter and quark matter coexist in layers or bubbles. Imagine a sponge where the solid portions are neutron matter and the empty spaces contain quark matter. The structure depends on surface tension between the two phases and various thermal effects. If neutron stars contain quark cores, the cores remain hidden beneath kilometers of neutron matter crust. Observing them directly is impossible with current technology. Instead, scientists look for indirect signatures. Quark cores might affect how neutron stars cool, how they spin, or how they respond to external forces. One key signature involves starquakes. Neutron star crusts can crack suddenly, releasing stored elastic energy. These quakes cause the star's spin rate to change abruptly. If a quark core exists below, the quake might trigger oscillations in the core fluid. Those oscillations would appear in the pulsar's radiation as characteristic modulations. Astronomers have detected several starquakes in pulsars. Analysis of the quake signatures provides clues about interior structure. Some quakes show patterns consistent with quark cores. Others seem to match pure neutron matter models. The data remains inconclusive but suggestive. Another test involves measuring how neutron stars cool over time. Young neutron stars born from supernovas start extremely hot. They radiate energy as neutrinos and photons, gradually cooling over millions of years. The cooling rate depends on internal composition and thermal conductivity. Quark matter cools through different processes than neutron matter. Quarks can emit neutrinos directly through weak interactions. This creates an efficient cooling channel that would cause quark stars to cool faster than pure neutron stars. Observing the temperature of neutron stars at various ages could reveal which cooling mechanism dominates. Recent observations found several young neutron stars that cooled extremely rapidly within their first 1,000 years. The cooling rates match predictions for direct neutrino emission from quark cores. This correlation suggests quark matter might indeed form in massive neutron star cores. However, alternative explanations exist. Neutron matter containing exotic particles like hyperons or condensates of pions could also cool rapidly. Without more detailed observations, distinguishing between these possibilities remains challenging. The strongest evidence for quark stars might come from finding objects too massive for pure neutron stars. Theory predicts maximum masses for neutron stars based on the properties of neutron matter. If an object exceeds this maximum, yet avoids collapsing to a black hole, it must contain something more than neutrons supporting it. Several confirmed neutron stars have masses near or slightly above theoretical limits for pure neutron matter. These massive objects push models to their breaking points. Including quark cores allows the maximum mass to increase by about 30%. This extended range could accommodate the heaviest observed neutron stars. What happens when quark matter forms an entire star from core to surface reveals nature at its most extreme. Unlike hybrid stars that contain both neutron matter and quark matter, strange stars would consist entirely of strange quark matter from center to surface. No neutron crust, no atomic nuclei, just bare quarks extending to the star's edge covered only by a thin layer of electrons. The possibility of such objects divides astrophysicists. Some models predict strange stars should be common, perhaps even more numerous than neutron stars. Other models suggest they cannot form at all. The truth lies hidden in quantum chromodynamics calculations, too complex to solve definitively. If strange stars exist, they would appear different from neutron stars in subtle ways. Both objects would have similar sizes, roughly 12 miles across. Both would possess powerful magnetic fields and rapid rotation. Both would emit X-rays and radio waves. Distinguishing them requires precise measurements of specific properties. Strange stars should have sharper edges than neutron stars. A neutron star's density decreases gradually from core to surface through layers of different matter phases. A strange star's density would drop nearly discontinuously. The bulk quark matter would extend almost to the surface, covered only by a thin electron atmosphere, perhaps 100 feet thick. This sharp boundary affects how the star appears in X-rays. Neutron star atmospheres contain atoms that absorb and emit radiation at characteristic wavelengths. Strange star atmospheres lack atoms entirely. Their X-ray spectra should show different patterns, possibly including features from free quarks interacting with photons. Some astronomers proposed several compact objects as strange star candidates. One famous case involves RxJ 1856, an isolated neutron star relatively close to Earth. Initial measurements suggested it appeared too small for its temperature, inconsistent with standard neutron star models. Strange star models fit the data better. Later observations complicated the picture. Different instruments obtained varying results. Some measurements supported the strange star interpretation. Others matched neutron star predictions. Currently, RxJ 1856 remains a possible strange star candidate, but far from confirmed. Strange stars might form through several mechanisms. A supernova core collapse under just the right conditions could create strange matter directly. The immense pressure and density during collapse might force quarks into the strange matter configuration. The resulting object would be born as a strange star. Alternatively, neutron stars might convert into strange stars over time. If a neutron star accretes enough material from a companion star, the added mass might push the core density past the threshold for strange matter formation. Once a seed of strange matter appears at the center, conversion might spread outward through the star. This conversion process should release enormous energy. Strange matter is more stable than neutron matter by assumption. Dropping from higher energy to lower energy liberates heat and radiation. The converting star would brighten dramatically, possibly producing a distinctive type of explosion. Astronomers have observed unusual cosmic events that might match converting neutron stars. Some gamma-ray bursts show characteristics inconsistent with standard models. Certain X-ray flares from compact objects display odd timing and spectra. These anomalies could represent neutron stars transforming into strange stars. The conversion rate depends on how efficiently strange matter nucleates inside neutron stars. If nucleation requires perfect conditions, conversion would be extremely rare. If nucleation happens easily above certain densities, many neutron stars might be strange stars or in the process of converting. One peculiar prediction involves strange star mountains. Normal neutron stars cannot support mountains more than a few millimeters high before gravity crushes them flat. Strange stars have much stronger surface cohesion because quark interactions bind the surface directly. This might allow mountains several inches tall, enormous by neutron star standards. These mountains would create asymmetries in the star's mass distribution. Rotating asymmetric masses generate gravitational waves continuously. Sensitive gravitational wave detectors might detect these signals from nearby strange stars. So far, continuous gravitational wave sources remain undetected, setting limits on possible mountain sizes. Another unique feature involves strange star crusts. Unlike neutron star crusts made of atomic nuclei, strange star crusts would consist of strange matter arranged in exotic structures. Strangelets might cluster together in crystalline patterns. The crust could alternate between layers of different quark arrangements. When strange star crusts crack during star quakes, the breaks would occur between strange matter domains rather than between nuclei. The acoustic properties and elastic behavior would differ from regular crusts. Detecting these differences through timing analysis of pulsars might reveal which objects are strange stars. Perhaps the most dramatic difference involves what happens when strange stars collide. Two neutron stars merging produce hot neutron matter that might collapse to a black hole or form a massive neutron star. Two strange stars colliding would produce hot, strange quark matter under extreme conditions. The merger might eject droplets of strange matter in all directions. Those droplets, if stable, would become strangelets propagating through the galaxy. Over cosmic timescales, strangelet density might build up in regions where strange star mergers are common. Our galaxy has existed for over 10 billion years. If strange stars are common and collisions are frequent, billions of strangelets might be drifting through interstellar space right now. Some could pass through our solar system. A few might even strike Earth, though their small size would make detection nearly impossible. The search for strange stars continues with improving technology. New X-ray telescopes offer better spectral resolution and sensitivity. Gravitational wave detectors become more precise with each upgrade. Radio telescope arrays can measure pulsar timing to nanosecond accuracy. Each advancement brings us closer to definitively identifying or ruling out these exotic objects. If strange stars do exist, their presence would revolutionize our understanding of matter under extreme conditions. It would confirm that quarks can exist in bulk outside normal particle confinement. It would validate entire branches of theoretical physics. It would open new questions about matter stability throughout the universe. But strange stars represent only one type of extreme stellar remnant. Others push the boundaries of physics in different directions. Earth has a magnetic field. Compasses detect it. It shields us from solar radiation. Its strength measures about half a Gauss at the surface. This field seems strong enough for its protective role. Now multiply that strength by 10,000 trillion. You reach magnetar territory. Magnetars are neutron stars with magnetic fields so powerful they warp quantum vacuum itself. These fields reach 1 quadrillion Gauss at the surface. At a distance of 600 miles, a magnetar's field would erase every credit card on Earth. It would disrupt cellular processes and potentially affect molecular bonds. Only about 30 confirmed magnetars exist in our galaxy. They form when neutron stars are born with extremely rapid rotation rates. The spin, combined with turbulent convection in the hot proto-neutron star, generates magnetic fields through a cosmic dynamo process. The fields trap and amplify during collapse, concentrating enormous flux. The resulting magnetic field stores energy equivalent to the star's rotational energy. This creates an unstable situation. The field wants to reconfigure to lower energy states. When it does, the stored energy releases explosively. Magnetar flares are the most violent electromagnetic events in the universe besides gamma-ray bursts. In less than a second, a magnetar can release more energy than our home star emits in 100,000 years. This energy erupts as X-rays and gamma rays that flood interstellar space. One particularly powerful flare in December 2004 originated from a magnetar about 50,000 light-years away. Despite the enormous distance, the radiation flash temporarily overloaded multiple satellites and affected Earth's ionosphere. If the magnetar had been only 10 light-years away, the flare might have caused mass extinction on Earth. The magnetic fields create bizarre effects near magnetar surfaces. Light does not travel straight through such strong fields. Photons split into two polarization modes that propagate at different speeds. This vacuum birefringence makes space itself optically active. Light beams bend and twist in ways impossible under normal conditions. Atoms cannot maintain normal structure in these fields. Electron orbitals become elongated into cigar shapes aligned with the field. Chemical bonds break or form differently. Matter becomes magnetically controlled at the atomic level. Even the vacuum exhibits strange behavior, with virtual particle pairs aligning before annihilating. The crust of a magnetar experiences unimaginable stress. Magnetic pressure tries to expand the star outward. Gravity tries to compress it inward. The two forces create strains that would shatter any normal material. The crust develops massive internal tensions that build over time. Eventually, something must give. The crust cracks suddenly in a star quake. The crack releases stored elastic energy and allows the magnetic field to reconfigure. Vast amounts of energy pour into accelerating particles and generating radiation. A magnetar flare erupts. These flares happen irregularly. Some magnetars go decades between outbursts. Others flare multiple times per year. The variability depends on internal structure and magnetic field evolution. Young magnetars tend to be more active as their fields and crusts settle into equilibrium. As magnetars age, their magnetic fields gradually decay. The mechanism involves electrical currents in the crust and core that can dissipate through resistance. Over millions of years, field strength decreases. The magnetar becomes less active and eventually resembles an ordinary pulsar. The interior of a magnetar might contain exotic matter formed under extreme magnetic influence. Some theories predict that strong fields could modify the phase diagram of nuclear matter. New types of matter with unusual properties could become stable. Quarks inside magnetars experience magnetic effects directly through their color charge. In sufficiently strong fields, quarks might align and organize differently than in ordinary neutron stars. This could trigger transitions to quark matter at lower densities than expected. One proposal suggests magnetar interiors could contain strange quark matter stabilized by magnetic fields. The combination of high density and high magnetic field might create conditions favorable for strange matter nucleation. The resulting hybrid structure would have both exotic composition and extreme magnetism. Observing magnetar interiors directly remains impossible. However, their spin behavior provides clues. Magnetars slow their rotation much faster than regular pulsars. This rapid spin-down suggests continuous energy extraction by the magnetic field. The field configuration and internal structure determine exactly how this energy extraction proceeds. Some magnetars show unexpected changes in their X-ray emission patterns. The variations might indicate shifting magnetic fields or changes in surface structure. Alternatively, they could result from matter transitioning between different phases inside the star. Distinguishing these possibilities requires detailed modeling and more observations. Recent discoveries found magnetars with lower magnetic fields than expected. These objects blur the line between magnetars and regular pulsars. Their existence suggests the magnetar phenomenon might be more common than previously thought, with a spectrum of field strengths rather than a sharp division. The origin of magnetars connects to other cosmic mysteries. Certain types of supernovas appear to produce magnetars preferentially. Very massive stars rotating rapidly before collapse might birth magnetars. The connection between progenitor properties and remnant type remains an active research area. Magnetars occasionally emit repeating radio bursts, similar to fast radio bursts detected from other galaxies. These magnetar giant flares might explain some extragalactic fast radio burst sources. If so, magnetars could be common throughout the universe, with their rare flares observable across cosmological distances. The existence of magnetars proves that nature can create conditions more extreme than anything achievable in laboratories. Their magnetic fields exceed human technology by factors of trillions. Their energy releases dwarf our most powerful devices. They operate in regimes where quantum electrodynamics becomes non-linear and vacuum itself gains properties. Understanding magnetars requires pushing physics to its limits, yet even more exotic objects might exist, formed not from stellar collapse but from the universe's first moments. The first stars did not light up until about 100 million years after the Big Bang. Before stars existed, before galaxies formed, before atoms assembled, tiny black holes might have appeared. These primordial black holes did not form from stellar collapse. No star existed to collapse. Instead, they condensed directly from density fluctuations in the extremely hot, dense early universe. Random quantum variations during cosmic inflation created regions slightly denser than their surroundings. When inflation ended, those overdense regions collapsed under their own gravity. The timing matters critically. During the first second after the Big Bang, the universe's density was enormous. Any fluctuation above a certain threshold would collapse immediately into a black hole. These primordial black holes could have any mass, from microscopic to millions of times our home star's mass, depending on when and how they formed. The lightest primordial black holes would have been truly tiny. A black hole with the mass of Mount Everest would measure only 1 nanometer across. One with the mass of a large asteroid would be about the size of a proton. These microscopic black holes would be far smaller than atoms yet contain more mass than mountains. Primordial black holes offer a possible explanation for dark matter, the invisible substance comprising 85% of the universe's matter. If many primordial black holes formed with masses between that of the Moon and our home star, they would be extremely difficult to detect individually, yet would gravitationally influence galaxies and galaxy clusters exactly as dark matter does. Testing this hypothesis involves several approaches. Gravitational microlensing can detect compact objects passing between Earth and distant stars. When a primordial black hole crosses our line of sight to a star, its gravity bends the starlight and causes brief brightening. Surveys monitoring millions of stars have found some candidate events. The frequency of microlensing events limits how much dark matter can be primordial black holes. If they comprised all dark matter, we would see more microlensing than observations reveal. Current data suggests primordial black holes might account for a few % of dark matter at most. Something else must dominate. Another test involves gravitational waves from black hole mergers. When LIGO detected colliding black holes with unexpected masses, some researchers proposed they might be primordial rather than stellar in origin. Stellar evolution struggles to produce black holes in certain mass ranges. Primordial formation has no such constraints. The debate continues. Some gravitational wave events favor primordial interpretations. Others clearly match stellar black holes. A mix seems likely, with some mergers involving primordial black holes and others involving stellar remnants. Separating the two populations requires detailed statistical analysis. Primordial black holes might explain other cosmic mysteries. Supermassive black holes at galaxy centers grew extremely quickly in the early universe. Standard formation scenarios struggle to explain such rapid growth. If primordial black holes served as seeds, the supermassive black holes could have started with substantial mass and accreted from there. Very small primordial black holes would have been extremely hot. Temperature increases inversely with mass for black holes. Microscopic black holes would radiate intensely, losing mass through Hawking radiation. The lightest ones would have evaporated by now. Any primordial black hole lighter than about 100 trillion kilograms would have completely radiated away its mass over the universe's 14 billion year lifetime. Only heavier ones survive to the present day. This evaporation sets a lower mass cutoff for detectable primordial black holes. We cannot find ones that formed too light because they no longer exist. The remaining population consists only of black holes massive enough to survive until today. Between the upper limit from microlensing and the lower limit from evaporation lies a window of masses where primordial black holes could hide. This window might contain enough primordial black holes to explain some dark matter observations while remaining below detection thresholds. Recent theoretical work explored whether primordial black holes could form in the first fraction of a second after the Big Bang. During cosmic inflation, quantum fluctuations might have created overdense regions that collapsed as soon as inflation ended. These ultra-early black holes would have unusual properties compared to later ones. The mass function of primordial black holes depends on the detailed physics of the early universe. Different inflation models predict different amounts at various masses. Observational constraints from multiple sources combine to rule out large regions of parameter space. Only certain formation scenarios remain viable. Some models predict primordial black holes should cluster together in dense groups. These clusters would behave like dark matter halos. Galaxies forming inside such halos would have primordial black holes scattered throughout. Occasional interactions between primordial black holes and stars might produce distinctive signals. The search for primordial black holes continues with improving sensitivity. New gravitational wave detectors can find lighter black hole mergers. Better microlensing surveys monitor more stars. Gamma-ray telescopes hunt for evaporation signatures. Each method constrains different mass ranges and formation scenarios. If primordial black holes exist, they represent the universe's oldest compact objects. They witnessed the entire history of cosmic evolution. They predate stars, galaxies, planets, and life itself. They are fossils from the Big Bang, floating through space, unchanged except for slow evaporation. Finding definitive proof of primordial black holes would revolutionize cosmology. It would confirm predictions about the early universe's conditions. It would validate aspects of inflation theory. It would provide a partial explanation for dark matter. It would demonstrate that black holes can form through mechanisms beyond stellar collapse. But the smallest primordial black holes face a dramatic fate that distinguishes them from all other black holes. A black hole with the mass of a small asteroid would measure smaller than a proton. Its event horizon would span about 1 femtometer, roughly the size of an atomic nucleus. This micro-black hole would contain more mass than Earth's largest mountains, compressed into a space tinier than a single atom. Such objects seem purely theoretical. No known natural process creates black holes this small. Stellar collapse produces black holes at least 3 times our home star's mass. Primordial formation during the Big Bang might have created smaller ones, but most would have evaporated by now through Hawking radiation. Yet, under specific conditions, micro-black holes could form briefly. When extremely high-energy particles collide, they might compress energy into small enough volumes to create temporary event horizons. Cosmic rays striking Earth's atmosphere at near light speed carry enormous energies, occasionally reaching levels that could, in principle, form micro-black holes. Particle accelerators were specifically designed to test this possibility. When the Large Hadron Collider began operations, some researchers predicted it might create microscopic black holes. These would not be dangerous. A micro-black hole would evaporate essentially instantly, far too quickly to consume any appreciable matter. The predictions depended on theories involving extra dimensions of space. If gravity becomes stronger at tiny distances due to hidden dimensions, then black holes could form at lower energies than expected. The collider's proton beams might have sufficient energy to create micro-black holes regularly. Experiments searched for characteristic signatures. Micro-black holes should decay through Hawking radiation into sprays of various particles. The decay products would appear as high-energy jets with specific statistical properties. Detectors analyzed millions of collisions looking for this pattern. No convincing micro-black hole signals appeared. Either the formation energy exceeds what colliders can achieve, or hidden dimensions do not exist, or black holes do not form in the predicted manner. The null result constrained theories about extra dimensions and quantum gravity. These non-detections tell us something important about nature. At the energy scales we can probe, gravity behaves according to Einstein's theory without significant modifications. Whatever exotic physics governs quantum gravity must wait for higher energies to manifest. Micro-black holes would possess peculiar properties if they could be created and studied. Their small size means their Hawking temperature would be enormous. Temperature scales inversely with mass. A black hole with mountain mass would have a temperature of billions of degrees. At such temperatures, the black hole radiates all types of particles: photons, electrons, quarks, neutrinos, and even heavier particles pour out as the black hole evaporates. The radiation spectrum follows a thermal distribution but with all particle types included. This makes micro-black hole radiation remarkably democratic, producing everything nature allows. The evaporation time depends on initial mass. A black hole with the mass of Mount Everest would completely evaporate in about 1 second. Smaller ones vanish faster, larger ones last longer. The relationship follows a cubic law. Double the mass and evaporation time increases 8-fold. This cubic relationship means very small differences in mass produce huge differences in lifetime. A black hole lasting 1 second has about 8 times the mass of one lasting half a second. The precise tuning required to make a black hole with any specific lifetime is extraordinary. Near the end of evaporation, the process accelerates dramatically. The black hole radiates faster as it shrinks. The temperature increases, driving even more radiation. Power output surges exponentially. In the final microseconds, the black hole releases as much energy as a nuclear bomb. This terminal explosion should produce a characteristic burst of high-energy gamma rays and particles. Satellites and ground telescopes search for such bursts, scanning the sky for sudden flashes matching the predicted spectrum. Finding even one would provide the first observational evidence for Hawking radiation. Decades of searching have produced no confirmed detections. The absence limits how many primordial black holes can be evaporating today. If they were common, we would see their death bursts regularly. The lack of signals means either primordial black holes are rare, or their mass distribution avoids the range that would be evaporating now, or Hawking radiation does not work as predicted. That last possibility seems unlikely but cannot be excluded entirely. Hawking radiation follows from combining quantum mechanics and general relativity in curved spacetime. The prediction seems solid theoretically. However, nobody has observed it directly from any black hole. Detecting Hawking radiation would confirm fundamental aspects of physics. It would prove that black holes emit thermally. It would validate the connection between gravity, quantum mechanics, and thermodynamics. It would provide evidence for processes occurring at the quantum gravity scale. The search continues with improving technology, but one recent cosmic event might have finally captured what scientists have sought for decades. Black holes trap everything. Light cannot escape. Matter disappears forever across the event horizon. This seemed absolute until 1974, when Stephen Hawking revealed something impossible. Black holes glow. The discovery emerged from combining quantum mechanics with general relativity. Near a black hole's event horizon, Quantum fluctuations create temporary particle pairs from empty space. Normally, these pairs annihilate immediately. But if one particle forms just inside the horizon while its partner appears just outside, they separate permanently. The particle outside escapes as real radiation. The particle inside falls into the black hole, carrying negative energy that reduces the hole's mass. From a distance, the black hole appears to emit particles and shrink slowly. Hawking called this thermal radiation. The effect seems impossibly weak for typical black holes. A black hole with our home star's mass would have a temperature of only 1/10,000,000th of a degree above absolute zero. The cosmic microwave background radiation is far warmer. Such black holes absorb more energy than they radiate. They grow rather than shrink. But smaller black holes radiate more intensely. Temperature increases as mass decreases. A black hole weighing as much as Mount Everest would glow at billions of degrees. One with Earth's mass would be barely warmer than the cosmic background. The crossover happens at specific masses where absorption and emission balance. For the first 40 years after Hawking's prediction, nobody observed this radiation from any black hole. The effect remained purely theoretical. Every black hole detected through telescopes or gravitational waves was far too massive to show measurable Hawking radiation. Their temperatures stayed essentially absolute zero. Then, in 2019, detectors captured an ultra-high energy neutrino unlike anything seen before. This ghost particle carried energy equivalent to several protons moving at nearly light speed. It came from outside our solar system, racing through space at almost maximum velocity. Researchers calculated backward from the neutrino's trajectory and energy. What could produce such a particle? Supernovas? Too weak? Active galactic nuclei? Wrong spectrum? Gamma-ray bursts? Inconsistent timing. Every conventional explanation failed to match the observations. One team proposed an extraordinary alternative. What if the neutrino came from a primordial black hole exploding in its final moments? As a micro black hole evaporates, it reaches a critical point where its remaining mass converts almost entirely to radiation. The terminal burst includes neutrinos at extreme energies. The mathematics align perfectly. A primordial black hole with specific initial mass, evaporating for billions of years, would reach its explosive finale at precisely the right moment to send that neutrino toward Earth. The energy spectrum matched predictions. The rarity matched expectations. This represents potentially the first detection of Hawking radiation, not from a laboratory experiment, not from astronomical observations of stellar black holes, from a microscopic black hole older than stars, completing its final act of self-destruction. The interpretation remains controversial. Other physicists suggest alternative sources for the ultra-high energy neutrino. Exotic cosmic ray interactions might produce similar signals. Unknown astrophysical processes could generate the required energies. The primordial black hole explanation fits but cannot be proven definitively from one event. Additional detections would strengthen the case dramatically. If more ultra-high energy neutrinos appeared with the predicted characteristics, the evidence would become compelling. Neutrino telescopes around the world now search specifically for these signatures. Finding even a handful of confirmed events would revolutionize physics. It would prove Hawking radiation exists. It would confirm primordial black holes formed in the early universe. It would validate decades of theoretical predictions. It would demonstrate that black holes truly evaporate rather than persisting forever. The search intensifies as detector sensitivity improves. Every ultra-high energy neutrino gets analyzed for possible primordial origins. Every gamma-ray burst gets examined for black hole evaporation signatures. Every cosmic ray shower gets checked against explosion models. What happens during the evaporation process reveals physics at its most fundamental level. Watch a black hole through time-lapse spanning billions of years. For eons, nothing changes. The hole maintains constant mass, constant size, constant temperature. Then, something shifts. the mass begins dropping. The horizon starts shrinking. The temperature climbs higher. This marks the transition from growth to death. Throughout most of cosmic history, black holes accumulate more mass than they radiate. Interstellar gas falls in. Cosmic microwave background photons cross the horizon. The hole gains weight faster than Hawking radiation removes it. Eventually, the universe expands enough and cools enough that this reverses. The cosmic background temperature drops below the black hole's Hawking temperature. Radiation output exceeds absorption. The black hole enters terminal evaporation mode. For stellar mass black holes, this transition lies unimaginably far in the future. A hole containing 3 times our home star's mass requires 10 to the 67th power years to evaporate completely. The current universe age measures only 14 billion years. Black holes will outlast stars, galaxies, and possibly protons themselves. But primordial black holes with smaller masses evaporate on human timescales. One weighing about 100 billion kilograms would last exactly until today. Anything lighter has already vanished. Anything heavier continues radiating. The evaporation follows a predictable curve. Mass decreases slowly at first. A black hole loses mass proportional to the inverse square of its current mass. Heavy holes shed mass glacially. Light holes evaporate rapidly. The process accelerates continuously. Plot mass versus time, and you get a curve plunging towards zero. The descent starts gentle, then becomes steep. In the final years, mass drops noticeably. In the final days, the decline becomes dramatic. In the final seconds, the black hole essentially explodes. During evaporation, the black hole radiates a thermal spectrum of particles. Everything nature allows emerges from the horizon. Photons dominate early, when the hole remains cool. As temperature rises, electrons and positrons appear. Higher still, and quarks join the mix. Near the end, even the heaviest particles radiate away. This democratic radiation has profound implications. Black holes erase information about what fell in. A hole formed from matter radiates the same as one formed from antimatter. An old hole from stellar collapse looks identical to a primordial hole formed from pure energy. The radiation carries no memory of initial conditions. This leads to the black hole information paradox. Quantum mechanics says information cannot be destroyed. Black hole evaporation seems to destroy it completely. Either quantum mechanics is wrong, or something about black hole evaporation preserves information, or the entire picture needs revision. Current theories propose various solutions. Maybe information leaks out gradually encoded in subtle correlations between emitted particles. Maybe it emerges in a final burst when the hole reaches Planck scale. Maybe it transfers to another universe or dimension. Maybe the paradox reveals flaws in combining quantum mechanics with gravity. The practical consequences affect observable physics. If information truly vanishes, then fundamental physical laws break down at black hole horizons. This would represent new physics beyond current understanding. Testing these ideas requires detecting and analyzing Hawking radiation directly. Evaporating black holes leave behind questions about remnants. When mass approaches the Planck scale, quantum gravity effects dominate. Standard physics breaks down. Some models predict the evaporation halts, leaving a stable Planck mass remnant. Others suggest complete evaporation to nothing. Nobody knows which is correct. These remnants, if they exist, would be extraordinarily dense and tiny. Each would weigh about 10 micrograms compressed to sizes smaller than atoms. They might be stable or slowly decaying. They might interact weakly or strongly with normal matter. They might constitute part of dark matter or contribute negligibly. Detecting such remnants seems nearly impossible. They interact only gravitationally at testable energies. Their small size makes direct collisions with detectors vanishingly rare. Their abundance depends on unknown early universe conditions. They could be everywhere or nowhere. The evaporation process also generates gravitational waves. As the black hole shrinks, its space-time curvature changes. These changes propagate outward as ripples in space itself. The gravitational wave signal encodes information about the hole's mass and spin throughout its lifetime. Future gravitational wave detectors might capture signals from evaporating primordial black holes. The waves would show characteristic frequency evolution as the hole loses mass. Combined with electromagnetic signatures, this multi-messenger approach could definitively prove Hawking radiation exists. But the most dramatic moment comes at the very end. The black hole weighs only grams now. Decades of steady evaporation have reduced it from mountain mass to pebble mass. The horizon measures smaller than atomic nuclei. Temperature soars into trillions of degrees. Radiation pours out at frantic rates. Each second strips away measurable fractions of remaining mass. The black hole glows blindingly across all wavelengths. Gamma rays, X-rays, ultraviolet, visible, infrared radiation all emerge simultaneously. Particles of every type spray outward in all directions. The temperature continues climbing. As mass decreases, Hawking radiation intensifies. The feedback loop accelerates. More radiation means faster. Mass loss means higher temperature, means even more radiation. The process enters runaway mode. In the final hour, half the black hole's mass converts to radiation. In the final minute, another quarter vanishes. In the final second, the last substantial fraction explodes outward. The curve plotting mass versus time approaches zero asymptotically, then terminates in a spike. The terminal burst releases energy equivalent to multiple nuclear weapons in a fraction of a second. All the remaining mass converts directly to radiation and particles. The explosion produces a brilliant flash visible across cosmic distances if instruments could detect it. The gamma-ray signature should be unmistakable. Theory predicts a specific spectral shape matching thermal radiation at extreme temperatures. The burst duration should correlate with initial black hole mass. Smaller holes explode faster. Larger holes take slightly longer. Neutrinos accompany the gamma rays. These ghost particles interact weakly with matter, allowing them to escape cleanly. Unlike gamma rays that might scatter on interstellar gas, neutrinos travel straight from explosion to detector. They provide unambiguous evidence of the event. The particle spectrum includes exotic species rarely seen in nature, top quarks, W bosons, Z bosons, Higgs particles, all emerge if the temperature reaches high enough. The terminal burst becomes a particle physics experiment, operating at energies exceeding any collider. Each explosion also generates gravitational waves. The black hole's mass distribution changes violently in the final moments. Space-time itself rings with gravitational radiation. The signal contains high-frequency components challenging to detect, but potentially observable with advanced instruments. Astronomers have searched for terminal bursts since Hawking first predicted them. Gamma-ray satellites monitor the entire sky continuously. When a burst appears, rapid analysis determines whether it matches primordial black hole explosions. So far, no definitive detections have occurred. The rarity depends on how many primordial black holes formed initially. If they were abundant, we should see multiple explosions per year. The absence of clear signals constrains how many can exist. Current limits suggest primordial black holes in the relevant mass range are quite rare. However, identifying terminal bursts among other gamma-ray phenomena proves difficult. Terrestrial lightning produces gamma rays. Solar flares generate bursts. Magnetars emit violent flashes. Distant supernovas create afterglows. Every candidate must be carefully analyzed to eliminate conventional explanations. One complication involves distance effects. A nearby explosion would be bright and easy to identify. A distant one would be faint and easily confused with background sources. Statistical analysis must account for volume effects and detection biases. The geometry of radiation emission matters too. If black holes do not radiate isotropically in their final moments, we might miss most explosions. Beaming effects could hide terminal bursts directed away from Earth. Only lucky alignment would make them visible. Some theoretical models predict multiple smaller bursts preceding the final explosion. As the black hole approaches Planck mass, quantum fluctuations might become violent. These fluctuations could cause episodic mass loss rather than smooth evaporation. The hole might stutter through its death throes. Finding even one confirmed terminal burst would provide invaluable data. Analyzing the spectrum would test quantum gravity theories. Measuring the duration would constrain primordial black hole formation models. Detecting associated neutrinos would prove Hawking radiation operates as predicted. The search continues with improving technology. Next-generation gamma-ray telescopes offer better energy resolution and sky coverage. Neutrino detectors grow larger and more sensitive. Gravitational wave observatories reach toward higher frequencies. Each advancement increases detection probability. If terminal bursts occur frequently enough, someone somewhere will eventually catch one. That moment will mark a revolution in fundamental physics. It will confirm predictions made 5 decades ago. It will prove that black holes are not eternal. It will show that nature operates in ways almost beyond imagination. And those ghost particles, emerging from dying black holes, tell their own story. Neutrinos barely interact with anything. A neutrino could pass through a light year of solid lead with only 50% chance of hitting something. Trillions pass through your body every second without you feeling the slightest effect. They are ghosts in the cosmic machine. Yet these ghosts carry information from the universe's most violent events. When a star explodes, neutrinos escape immediately, while light takes hours to break free. When black holes collide, neutrinos might reveal hidden physics. When primordial black holes explode, neutrinos could be the smoking gun. The terminal burst from an evaporating black hole produces neutrinos across a huge energy range. Low-energy neutrinos, at millions of electron volts, emerge when the hole still weighs kilograms. Medium-energy neutrinos at billions of electron volts appear as mass drops to grams. Ultra-high-energy neutrinos at trillions of electron volts explode outward in the final microseconds. These ultra-high-energy neutrinos stand out because nothing else produces them abundantly. Natural radioactivity generates low-energy neutrinos. Nuclear reactions in stars make medium-energy neutrinos. Cosmic ray interactions create moderately high-energy neutrinos, but ultra-high-energy neutrinos require extreme processes. Detecting them requires enormous instruments. Neutrino observatories use thousands of tons of ultra-pure water or ice as target material. When a neutrino finally interacts, it produces a flash of light detected by surrounding sensors. The light pattern reveals the neutrino's direction and energy. IceCube, a detector using 1 cubic kilometer of Antarctic ice, captured the suspicious ultra-high-energy neutrino in 2019. The event deposited enough energy to be clearly visible despite neutrinos' weak interactions. Analysis showed the particle came from deep space, not Earth's atmosphere. Calculating backward from its trajectory and energy, researchers proposed it might have originated from a primordial black hole exploding within a few hundred light-years of Earth. The timing, energy, and rarity all matched predictions for terminal burst neutrinos. Other explanations remain possible. Active galaxies occasionally accelerate particles to extreme energies. Gamma-ray bursts might produce ultra-high-energy neutrinos. Unknown cosmic accelerators could exist. The primordial black hole interpretation fits well but cannot be proven from one event. Finding more such neutrinos would strengthen the case. If several appeared with characteristics matching evaporation models, coincidence becomes unlikely. The statistical significance would grow with each detection. Eventually, the evidence would become undeniable. IceCube and similar detectors now actively search for terminal burst signatures. When ultra-high-energy neutrinos appear, rapid analysis checks for correlations with gamma-ray bursts or other astronomical events. The goal is catching a synchronized flash and particle burst from the same explosion. Future detectors will offer better sensitivity. Proposals include expanding IceCube to multiple cubic kilometers. Pacific Ocean detectors could monitor additional sky regions. Space-based neutrino observatories might track ultra-high energy events from orbit. Each improvement increases discovery chances. The neutrino spectrum from terminal bursts should show distinctive features. As the black hole radiates through various mass ranges, different particles dominate emission. Early phase produces mostly photons. Middle phase adds electrons and positrons. Final phase includes all standard model particles. Neutrinos emerge throughout, but with varying flavors and energies. Electron neutrinos, muon neutrinos, and tau neutrinos all appear. Their relative abundances depend on the black hole's temperature at each moment. This creates a fingerprint potentially identifiable in detector data. One challenge involves background sources. Atmospheric neutrinos from cosmic ray interactions create continuous noise. Distant astrophysical sources contribute sporadic events. Terrestrial radioactivity adds low-energy background. Separating genuine terminal burst signals requires careful analysis. Machine learning algorithms now assist in event classification. Neural networks trained on simulated data can identify patterns characteristic of black hole explosions. These tools flag suspicious events for detailed human review, increasing efficiency. The payoff for finding terminal burst neutrinos extends beyond confirming Hawking radiation. The neutrino data would constrain quantum gravity effects. Black holes near Planck mass enter regimes where space-time itself fluctuates quantum mechanically. Neutrino spectra encode these effects. Different quantum gravity theories predict slightly different terminal burst characteristics. String theory suggests one pattern. Loop quantum gravity predicts another. Observing actual explosions would test which approach better describes nature at its smallest scales. This connects black hole physics to particle physics in unexpected ways. The standard model might be incomplete. New particles beyond known types could exist. Terminal bursts operating at ultra-high energies would produce these hypothetical particles if they are real. Finding unexpected particles in terminal burst data would revolutionize physics. It would prove new physics beyond current theories. It would guide construction of future particle colliders. It would open entire new research directions. The ghost particles from dying black holes might ultimately reveal the deepest truths about reality. They connect the universe's largest structures to its smallest components. They bridge gravity and quantum mechanics. They demonstrate that nothing, not even black holes, lasts forever. And those same black holes might solve another cosmic mystery. Galaxies spin too fast. Stars orbit galactic centers at speeds that should fling them into intergalactic space. Yet galaxies hold together. Something invisible provides extra gravitational pull. We call it dark matter. 5 times more dark matter exists than normal matter. It surrounds galaxies in enormous halos. It permeates galaxy clusters. It shaped cosmic structure formation. Yet nobody knows what it is made of. Decades of searching have not identified the particle or particles responsible. Primordial black holes offer one solution. They gravitationally affect their surroundings identically to dark matter. They interact only through gravity. They formed early enough to seed galaxy formation. They exist across a range of masses that could explain observations. The idea seems almost too simple. Why invent exotic particles when ordinary black holes could work? Why propose new physics when general relativity already predicts everything needed? Primordial black holes solve the dark matter mystery using established physics. But several observations constrain how much dark matter can be black holes. Gravitational microlensing searches have surveyed millions of stars for brief brightening events caused by compact objects passing through the line of sight. The detection rate limits black hole abundance. Current microlensing data excludes primordial black holes as dominant dark matter in certain mass ranges. Too few events occur to account for all dark matter with black holes between 1/10 and 10 times our home star's mass. However, lighter and heavier ranges remain allowed. Black holes with masses between Earth's mass and 1/10 our home star's mass evade most constraints. They are too heavy to have evaporated. too light to produce frequent microlensing, and form at just the right time to seed cosmic structure. This window might contain enough primordial black holes to explain dark matter. Testing this requires new observational approaches. Gravitational wave detectors might capture mergers between primordial black holes in this mass range. Next-generation microlensing surveys, with better sensitivity, could detect smaller black holes. Orbital dynamics of distant stars might reveal nearby primordial black holes. Another test involves ultra-faint dwarf galaxies. These tiny galaxies contain far more dark matter than normal matter. If dark matter consists of primordial black holes, occasional close encounters between black holes and stars should occur. These encounters would disrupt the dwarf galaxy's structure in observable ways. Current data shows no clear disruption signatures. This suggests either primordial black holes are less abundant than required to be all dark matter, or they cluster less than expected, or the encounters do not produce the predicted effects. Very light primordial black holes, with masses similar to asteroids, evade all current direct constraints. They are too small for microlensing, too light to merge detectably, too weakly interacting for most observations. They could comprise significant dark matter fractions without contradicting existing data. However, these light black holes would emit substantial Hawking radiation. Collectively, millions or billions of them radiating throughout the galaxy would produce a diffuse gamma-ray background. Measurements of this background limit how many can exist. The constraints tighten as detector sensitivity improves. Another possibility involves black hole clusters. If primordial black holes formed in groups rather than individually, the clusters would act as extended dark matter halos. Individual holes within clusters would interact gravitationally, creating complex dynamics. The clusters might explain galactic structure better than uniform dark matter distributions. Simulations of galaxy formation with primordial black hole dark matter show both successes and challenges. The black holes cluster gravitationally as required. They seed galaxy formation appropriately. But some predictions mismatch observations. Small-scale structure appears different than expected. Galaxy masses show unexpected correlations. These discrepancies might indicate primordial black holes cannot be all dark matter, or perhaps they point to incorrect assumptions in simulation parameters. Or maybe both primordial black holes and particle dark matter coexist, each contributing some fraction. The mixed scenario has appeal. Perhaps 70% of dark matter consists of unknown particles, while 30% is primordial black holes. This would explain why particle searches have not succeeded yet. The dark matter is genuinely mixed, requiring multiple detection strategies. Recent intriguing observations add complexity. Ultra-high energy cosmic rays appear to come from no identifiable sources. Their trajectories point toward empty space. If primordial black holes populate dark matter halos, occasional particles accelerated near their horizons could produce these mysterious cosmic rays. Some gamma-ray signals from the galactic center show unexpected characteristics. Standard dark matter models struggle to explain them. Primordial black hole models fit better. The radiation could come from many small black holes throughout the galactic halo rather than from a single central source. The James Webb Space Telescope discovered surprisingly massive galaxies in the very early universe. Standard dark matter models predict galaxies should grow more slowly initially. If massive primordial black holes seeded these early galaxies, rapid growth becomes possible. Each observation adds pieces to a complex puzzle. No single explanation accounts for all data perfectly. The truth might involve combinations nobody has considered fully. Primordial black holes could be some dark matter, or none, or all of it under specific conditions. Resolving the question requires continued observations across multiple channels. Gravitational waves, gamma rays, cosmic rays, microlensing, and galactic dynamics all provide independent constraints. As data accumulates and simulations improve, the parameter space for primordial black hole dark matter shrinks. Eventually, either sufficient evidence will confirm primordial black holes as dark matter, or tight constraints will exclude them completely. Either outcome advances understanding. We will either know what dark matter is, or know what it definitely is not. But primordial black holes connect to other cosmic mysteries through the most energetic particles in existence. A proton slams into Earth's upper atmosphere. Its speed approaches light velocity so closely that time itself dilates. This single proton carries energy equivalent to a baseball thrown at 60 miles per hour. Condensing that much energy into one subatomic particle requires processes operating at extremes. We call these cosmic rays. They arrive constantly from all directions. Most carry moderate energies. Some reach extraordinary levels. The most energetic ones challenge everything we know about particle acceleration. Their origin remains one of astrophysics' deepest mysteries. Standard acceleration mechanisms struggle to explain ultra-high energy cosmic rays. Supernovas can accelerate particles to high energies but not ultra-high. Active galactic nuclei seem promising but too distant. Gamma-ray bursts might work but occur too rarely. Every conventional candidate faces problems. Primordial black holes offer one intriguing explanation. As these black holes evaporate, they emit particles across enormous energy ranges. The final death throes produce particles at ultra-high energies, matching the mysterious cosmic ray observations. Calculate the expected flux from evaporating primordial black holes scattered throughout our galaxy. If enough black holes exist in the relevant mass range, their collective emissions could account for observed ultra-high energy cosmic rays. The spectrum, arrival directions, and particle types all match reasonably well. One key test involves chemical composition. Cosmic rays from normal astrophysical sources should be primarily protons with some heavier nuclei. Terminal bursts from black holes should produce equal numbers of all particle types initially, though interactions in interstellar space modify the ratios. Current cosmic ray detectors analyze composition by measuring how particle showers develop in the atmosphere. Ultra-high energy events show unexpected patterns. Some showers look proton-like. Others resemble heavier nuclei. The mixture does not match simple source models. Primordial black hole explosions might explain this diversity. Different explosions occur at different times and distances. Particles from each explosion propagate through interstellar space differently. The resulting mix arriving at Earth naturally shows varied composition. Another mystery involves arrival directions. Ultra-high energy cosmic rays do not correlate strongly with obvious sources. They do not point back toward the galactic center or toward known active galaxies. Their directions appear nearly random despite their extreme energies. This randomness actually supports the primordial black hole hypothesis. If black holes scatter throughout galactic dark matter halos, their explosions would occur everywhere. No preferred direction would emerge. The cosmic rays would seem to come from nowhere specific. Magnetic fields complicate interpretation. Charged particles deflect in galactic and intergalactic magnetic fields. Ultra-high energy particles deflect less than low-energy ones, but still deflect measurably. Tracing cosmic rays back to their sources requires modeling these magnetic effects. When researchers include realistic magnetic field models, some ultra-high energy cosmic ray trajectories could originate from nearby primordial black hole explosions. A black hole exploding within a few thousand light-years would produce particles reaching Earth with the correct energies and arrival times. The telescope array in Utah and the Pierre Auger Observatory in Argentina monitor ultra-high energy cosmic rays continuously. Both detect roughly 1 particle per square kilometer per century at the highest energies. This rate constrains source populations and emission mechanisms. If primordial black holes generate these cosmic rays, the detection rate implies a specific evaporation rate and black hole population. Working backward from observations gives estimates of how many primordial black holes exist in our galactic neighborhood. The numbers are small, but not impossibly so. One recent event particularly puzzled researchers. In 2021, a cosmic ray detected in Utah carried energy exceeding 240 exelectron volts. This surpasses previous records significantly. No known astrophysical object produces such energies easily. A primordial black hole exploding relatively nearby could generate this event. The particle would be one photon or hadron from a terminal burst, accelerated to maximum energy in the final microseconds before the black hole vanished. Most burst particles spread widely, but a few might happen to aim directly toward Earth. Statistical analysis shows such events should be rare. One per decade fits expectations for primordial black holes in permitted mass ranges. More frequent detections would overconstrain the population. Less frequent observations would suggest alternative sources dominate. Future cosmic ray experiments will improve both sensitivity and angular resolution. Better tracking cosmic rays to their sources will test the primordial black hole hypothesis directly. If trajectories cluster toward regions where black holes might hide, evidence strengthens. Random arrivals from nowhere support the hypothesis. Ground-based detectors face limitations. They observe only cosmic rays that reach Earth. Particles from distant explosions might never arrive here. Comprehensive surveys require space-based missions covering larger solid angles and longer time periods. Proposed space missions include cosmic ray monitors on satellites and detectors on the Moon. Lunar instruments would observe from a stable platform without atmospheric interference. They could track ultra-high energy events with unprecedented precision. Connecting cosmic ray observations with gravitational waves and electromagnetic signals would provide definitive tests. Multi-messenger astronomy allows cross-checking different detection channels against each other. A coincident detection across multiple channels would prove primordial black hole origins conclusively. But cosmic rays represent only one mystery. Exotic star surfaces might harbor even stranger phenomena. Neutron stars have crusts made of atomic nuclei compressed into crystalline lattices. Strange stars, if they exist, possess something far more exotic. Their surfaces consist of strangelets arranged in patterns, impossible under normal conditions. The crust of a strange star would not be crust in the familiar sense. No atoms, no nuclei, no ordinary matter at all. Instead, the surface consists of strange quark matter transitioning from liquid interior to vacuum exterior. This boundary region organizes into complex structures. Surface tension plays a crucial role. Strange matter might have low surface tension, allowing it to fragment into small droplets easily. These strangelet droplets would hover above the main quark liquid, held by complex electromagnetic and gravitational forces. The result resembles exotic foam or structured plasma. Some models predict crystalline strangelet arrangements. The strangelets might pack into geometric patterns like atoms in a crystal. Each strangelet interacts electromagnetically with neighbors through their electron atmospheres. The stable configuration minimizes total energy, creating ordered structures. These crystalline crusts would be extraordinarily thin, perhaps only meters thick on a star measuring 12 miles across. Below the crust, bulk strange matter extends continuously to the star's center. Above the crust, a thin atmosphere of electrons neutralizes the surface charge. The crust's properties determine how the star appears in different wavelengths. X-ray emission depends on surface temperature and composition. Radio emission connects to magnetic field configuration. Optical observations could theoretically detect reflection from crust structures. One distinctive signature involves crust quakes. When strange star crusts crack, they do so differently than neutron star crusts. Strangelet crystals reorganize rather than breaking between nuclear domains. The energy release follows different scaling laws. The timing and magnitude of quakes could distinguish star types. Pulsars show occasional glitches where their rotation rates suddenly jump. These glitches result from crust failures and subsequent spin-up events. Strange stars might produce glitches with characteristic timescales and magnitudes differing from neutron stars. Careful timing analysis could reveal these differences. Another test involves magnetic field evolution. Neutron star crusts contain superconducting regions that pin magnetic field lines. Strange star crusts might behave differently. Field lines could move more freely or anchor more strongly depending on crust composition. Magnetic field decay rates provide clues. The electron atmosphere above a strange star crust should be extremely thin, perhaps only 100 feet thick. Below this atmosphere, bare quark matter directly contacts vacuum. Above it, empty space extends to interstellar distances. This sharp transition affects light emission. Photons escaping from the surface pass through the electron layer. Some wavelengths absorb strongly, others transmit freely. The resulting spectrum shows unusual features, potentially detectable with sensitive X-ray telescopes. Comparing spectra from candidate strange stars to neutron star predictions could identify differences. Temperature affects surface structure dramatically. Hot, strange stars might have liquid surfaces. Cool ones might develop solid crusts. The transition temperature depends on interstrangelet interactions and pressure conditions. Different models predict transitions occurring at different temperatures. Observing strange stars across a range of ages would test thermal evolution models. Young, hot, strange stars should look different from old, cool ones. The progression of surface properties with age provides diagnostics unavailable from single observations. Some theoretical work suggests strange star crusts might be unstable to collapse. If a certain critical mass accumulates on the surface through accretion, the crust could suddenly fail. The collapse would trigger violent energy release as material falls onto the bulk strange matter below. This collapse mechanism has been proposed to explain fast radio bursts. When a strange star crust fails, the sudden energy release accelerates electrons to extreme energies. These electrons radiate coherent radio waves as they stream through the star's magnetic field. The result is an intense radio pulse, lasting milliseconds. Several fast radio burst properties match strange star crust collapse predictions. The burst energies, durations, and repeat patterns all align reasonably well. However, alternative models involving magnetar flares also explain the observations. Distinguishing these scenarios requires additional data. If strange stars exist abundantly, their peculiar crust properties should appear in statistical studies. Comparing populations of compact objects might reveal subgroups with distinct surface characteristics. These subgroups could represent strange stars versus neutron stars. Current data shows possible hints of such divisions. Some compact objects cool faster than expected. Others show unusual glitch behavior. A few display X-ray spectra difficult to explain with standard models. Each anomaly might indicate strange star identification. However, exotic neutron star physics could also explain these anomalies. Superfluid interiors, strong magnetic fields, and unusual compositions can produce unexpected observational signatures. Definitively proving strange star existence requires finding multiple independent indicators consistent only with quark surfaces. Future X-ray missions will provide the sensitivity needed for detailed spectroscopy. Measuring precise absorption and emission features from compact object surfaces will test whether bare quark matter signatures appear. The detection would be subtle, requiring careful analysis and sophisticated modeling. Meanwhile, theoretical work refines predictions about how strangelet crusts should behave. Computer simulations model interactions between millions of strangelets under various conditions. The results guide observers toward the most diagnostic measurements. The crusts themselves rest atop bizarre quantum effects occurring near black hole horizons. Stand at a black hole's event horizon and quantum mechanics goes haywire. Virtual particles that normally wink in and out of existence separate permanently. Vacuum energy density fluctuates wildly. Space-time itself exhibits quantum uncertainty. Physics enters truly unexplored territory. The horizon represents a boundary in space where gravity becomes so strong that not even light escapes. Mathematically, it is a smooth surface with no special properties locally. An observer falling through would notice nothing unusual at the crossing point, yet viewed from outside, the horizon displays extraordinary quantum behavior. Quantum field theory predicts that empty space constantly produces particle-antiparticle pairs. These virtual pairs borrow energy from vacuum uncertainty, exist briefly, then annihilate. The process happens everywhere continuously. Near black hole horizons, it leads to something remarkable. When a virtual pair forms very close to the horizon, they might separate before annihilating. One particle falls inward across the horizon, the other escapes outward. To external observers, the black hole appears to emit a real particle. This is Hawking radiation emerging from quantum fluctuations. The process seems to violate energy conservation. A particle escapes carrying positive energy. Where does this energy come from? The answer involves subtle quantum mechanical bookkeeping. The infalling particle carries negative energy from the horizon's perspective, slightly reducing the black hole's mass. This negative energy remains controversial conceptually. How can particles have negative energy? The resolution lies in understanding energy as a relative quantity. What appears as negative energy to one observer appears differently to others. The horizon creates circumstances where these relativistic effects become crucial. Calculating Hawking radiation precisely requires quantum field theory in curved spacetime. The equations combine general relativity's description of gravity with quantum mechanics' description of matter. Solving these equations remains extremely difficult except for simple black hole geometries. For rotating or electrically charged black holes, the calculations become vastly more complex. The horizon structure changes. Multiple horizons might appear. The quantum field behavior varies depending on spin and charge. Each situation requires separate analysis. Near rotating black hole horizons, frame dragging effects intensify. Spacetime itself rotates, pulled by the black hole's spin. Virtual particles created here experience this rotation. The emission becomes asymmetric, with more particles emerging along the rotation axis than the equator. Electrically charged black holes introduce additional complications. The horizon carries electric charge. This affects how virtual particles' pair production occurs. Charged particles feel electromagnetic forces in addition to gravity. The resulting Hawking radiation spectrum differs from uncharged black holes. Quantum effects also produce fluctuations in the horizon's position. The event horizon is not a fixed surface, but a statistical average. Quantum uncertainty causes it to jitter by tiny amounts. For stellar mass black holes, the jitter measures far smaller than atomic nuclei. For microscopic black holes, fluctuations become comparable to the horizon size itself. These fluctuations might encode information about what fell into the black hole. Some theories suggest information leaks out through subtle correlations in the jittering. This could resolve the black hole information paradox by showing information is not truly lost. Another quantum effect involves particles tunneling through the horizon. Quantum mechanics allows particles to appear in classically forbidden regions. A particle inside the horizon might quantum tunnel outward, escaping despite insufficient classical energy. This tunneling contributes to Hawking radiation alongside virtual pair creation. The horizon also exhibits quantum entanglement effects. Particles inside and outside the horizon can remain quantum mechanically entangled. Measuring one particle instantly affects the other, despite being separated by the horizon. This non-local connection raises deep questions about causality and information flow. Some physicists propose the horizon might be a firewall of high-energy particles. This controversial idea suggests quantum effects at the horizon create violent radiation that would incinerate anything falling through. It attempts to resolve the information paradox, but contradicts general relativity's prediction of a smooth horizon. The firewall debate highlights how little we understand quantum gravity. At the horizon, quantum mechanics and general relativity clash. Each theory says different things about what happens. Neither alone provides a complete description. A theory of quantum gravity is needed. String theory offers one approach to quantum gravity. It replaces point particles with tiny vibrating strings. Applied to black holes, string theory predicts the horizon has microstructure. What appears smooth classically consists of many quantum degrees of freedom at microscopic scales. Loop quantum gravity provides an alternative. It quantizes space-time itself, replacing continuous geometry with discrete quantum chunks. Black hole horizons, in this framework, consist of quantum geometric states. The horizon becomes a quantum mechanical object with specific discrete properties. Both approaches predict modifications to Hawking radiation at extreme scales. The corrections remain tiny for stellar mass black holes. For Planck-scale black holes, the corrections dominate. Observing terminal explosions from evaporating primordial black holes might test which quantum gravity approach is correct. The horizon also serves as a laboratory for testing holographic principles. These principles suggest that all information in a region of space can be encoded on its boundary. The black hole horizon acts as such a boundary, potentially containing all information about the interior. If holography is correct, then studying horizon quantum effects reveals fundamental truths about space and information. The horizon is not just a physical boundary, but an informational one. Everything that falls in leaves an imprint on the horizon's quantum state. But detecting any of these quantum effects requires observations at currently impossible precision levels. Finding the rarest things in the universe means detecting signals almost indistinguishable from background noise. Every candidate observation faces skepticism. Every measurement sits at the edge of instrument capabilities. Every detection requires extraordinary evidence. Antimatter detection illustrates the challenges. Creating and storing antimatter in particle accelerators is one thing. Detecting natural antimatter in space is vastly harder. Antiparticles look nearly identical to normal particles in most observations. Distinguishing them requires precise measurements. Satellite detectors search for cosmic ray antiparticles by measuring how particles curve in magnetic fields. Positively charged particles bend one way. Negatively charged particles bend the opposite way. This distinguishes positrons from electrons and antiprotons from negative particles. But cosmic rays include many particle types with various charges. Background contamination remains high. False positives occur. Extended observation time with excellent statistics becomes necessary. Years of data accumulation provide enough events for meaningful analysis. Astatine detection faces different problems. The element decays so rapidly that isolating macroscopic samples is impossible. Every astatine atom must be artificially created, then studied within hours before it vanishes. The experiments require particle accelerators synchronized with analytical equipment. Producing individual astatine atoms is relatively straightforward. Detecting and characterizing them pushes technology limits. Each atom might decay before measurements complete. Statistical analysis requires creating many atoms and averaging results across all observations. Strange quark matter detection presents perhaps the greatest challenge. No confirmed samples exist anywhere. Theoretical predictions guide searches. But what if theory is wrong? What if strange matter behaves differently than expected? Null results might mean the substance does not exist, or that detectors cannot see it. Searches for strangelets in cosmic rays look for particles with unusual mass to charge ratios. Normal nuclei follow predictable patterns. A strangelet would deviate dramatically. Its mass would far exceed any nucleus with the same charge. This signature should be unmistakable. Yet decades of cosmic ray monitoring have not produced convincing strangelet candidates. Either they are extraordinarily rare, or they interact with detection equipment in unexpected ways, or they simply do not exist. Distinguishing these possibilities requires better instruments and longer observation times. Primordial black holes evade detection through multiple mechanisms. They emit no light, they make no sound. Their gravitational effects are tiny unless something passes very close. They hide in plain sight, invisible against the cosmic background. Gravitational microlensing offers one detection method. When a black hole passes between Earth and a distant star, its gravity bends the starlight and causes brief brightening. Monitoring millions of stars constantly might catch a few events per year. Each event must be analyzed carefully to confirm its origin. The alternatives include planets, brown dwarfs, stars, and normal black holes. Distinguishing primordial from stellar black holes requires measuring the lens mass. This comes from analyzing the light curve shape. Precision photometry over the entire event duration provides the needed data. Magnetar detection is easier because they actively emit radiation. Yet identifying which neutron stars are magnetars requires observing flares or measuring magnetic field strength. Both measurements face technical difficulties. Magnetic fields cannot be measured directly from Earth. Indirect indicators provide estimates. X-ray satellites monitor known magnetars for flare activity. When flares occur, rapid response observations capture detailed spectra. The timing, energy distribution, and evolution provide clues about magnetic field structure and interior composition. Combining observations across multiple wavelengths improves understanding. Hawking radiation detection faces enormous difficulties because the effect is so weak. Stellar mass black holes radiate at temperatures barely above absolute zero. Their emission is completely swamped by cosmic microwave background. Finding the signal requires looking at the right black holes at the right times. Terminal bursts from evaporating primordial black holes offer the best detection opportunity. These bursts should be bright enough to see across cosmic distances. However, they must be distinguished from other energetic transient phenomena. Gamma-ray bursts from dying massive stars look superficially similar. Magnetar flares produce comparable energies. Neutron-star collisions generate similar radiation. Each possibility must be eliminated through detailed spectral and timing analysis. Multi-messenger observations provide the strongest constraints. Simultaneously detecting gravitational waves, neutrinos, and electromagnetic radiation from the same event pins down its nature. The combined information eliminates most ambiguities. Future detection capabilities depend on next-generation instruments. Larger gravitational wave detectors will sense weaker signals from farther away. More sensitive gamma-ray telescopes will capture fainter, transient events. Improved neutrino observatories will detect more ultra-high energy particles. Each technological advance opens new discovery space. Phenomena currently invisible might become routine observations. The rarest things gradually reveal themselves as our tools improve. What seems impossible today becomes standard tomorrow. But some things might remain forever beyond detection limits imposed by fundamental physics. Physics imposes absolute boundaries on what can exist. Not all imaginable objects are possible. Not all combinations of properties can occur simultaneously. Theory provides ironclad reasons why certain things must remain forbidden forever. Consider stable elements heavier than uranium. As atomic number increases, nuclear instability grows. Protons packed together repel each other electromagnetically. Beyond a certain size, the repulsion overcomes the strong force binding. The nucleus flies apart. Theory predicts an island of stability at atomic numbers around 114. Special combinations of protons and neutrons might achieve temporary stability, but even these islands sink eventually. Atoms significantly heavier cannot exist for more than fractions of seconds. Similarly, neutron stars have maximum masses, above approximately 3 times our home star's mass. No known force can prevent gravitational collapse. Neutron matter reaches its strength limit. Quark matter reaches its limit. Something must give. The star collapses to a black hole inevitably. This mass limit applies even to exotic matter. Strange quark stars might be slightly heavier than neutron stars. Hypothetical quark matter phases could push limits marginally higher, but fundamental physics constraints remain. Above certain masses, collapse cannot be prevented by any form of matter. Black holes themselves face limits. The smallest possible black hole masses about 10 micrograms at the Planck scale. Below this mass, quantum gravity effects dominate. The concept of a classical horizon breaks down. Whether smaller black holes can exist depends on unknown quantum gravity physics. At the opposite extreme, black holes cannot exceed the mass of the observable universe. Such an object would contain everything within its event horizon. Nothing would exist outside. The concept becomes self-contradictory. Observable reality places an upper bound on black hole masses. Temperature has absolute limits too. Nothing can be colder than absolute zero by definition. But maximum temperature also exists. At the Planck temperature, roughly 10 to the 32nd power degrees, space-time itself breaks down. Thermal fluctuations become so violent that quantum gravity effects dominate. Temperature loses its conventional meaning. Density faces similar bounds. Nuclear density represents a practical upper limit for normal matter. Neutron stars push toward this limit. Quark stars might slightly exceed it. But eventually, gravitational collapse becomes unavoidable. Stable matter cannot achieve arbitrarily high density. Even information has limits. The Bekenstein bound states that any physical system contains finite information proportional to its surface area. A black hole saturates this bound. Nothing can store more information per unit area than a black hole. This connects thermodynamics, quantum mechanics, and gravity in profound ways. These limits are not merely technological, they are fundamental. No advanced civilization could overcome them. No exotic physics could circumvent them. They follow from the basic laws of nature as we understand them. Some proposed particles violate these limits and therefore cannot exist. Faster than light particles, called tachyons, would create causality paradoxes. Magnetic monopoles with certain properties would violate charge conservation. Particles with imaginary mass would make vacuum unstable. Physics journals receive numerous proposals for impossibilities: perpetual motion machines, free energy devices, anti-gravity systems. Each violates conservation laws or thermodynamics principles. Peer review rejects them not from closed-mindedness, but from rigorous analysis showing internal contradictions. However, some limits might be less absolute than they appear. Quantum mechanics allows tunneling through energy barriers. Particles can briefly borrow energy from vacuum uncertainty. Black holes evaporate eventually. What seems forbidden classically might occur quantum mechanically with low probability. This distinction matters for the rarest phenomena. If something has any non-zero probability, given enough time and space, it must occur somewhere. The universe is vast and old. Rare events happen. Improbable configurations arise. Statistical mechanics guarantees unusual fluctuations. The question becomes whether probabilities are merely tiny or exactly zero. Antimatter exists but is rare. Strange quark matter might exist in specific environments. Primordial black holes could populate dark matter halos. Each phenomenon has finite probability. True impossibilities have exactly zero probability, regardless of circumstances. They violate conservation laws that hold absolutely. They contradict logic itself. They create paradoxes that cannot be resolved. These remain forever theoretical curiosities. Distinguishing between extraordinarily rare and truly impossible requires careful analysis. Mathematical proofs establish impossibility conclusively. Observational null results only constrain probability. The absence of evidence is not evidence of absence for sufficiently rare phenomena. This philosophical point underlies searches for the universe's rarest things. We do not know in advance whether something exists until we look. Theory guides searches by predicting where and how to look, but nature might surprise us with unanticipated phenomena. Each discovery of something once thought impossible expands our understanding. Antimatter was theoretical until detected. Black holes were mathematical curiosities until observed. Gravitational waves remained speculative until measured directly. The possible becomes real through persistent observation. The truly impossible remains impossible, but the merely extraordinarily rare might be discovered tomorrow. This hope drives researchers to continue searching, pushing instruments to their limits, analyzing data with unprecedented care. Somewhere in the vast universe, the rarest things await discovery. And when we combine all these rare phenomena, we approach the ultimate limits of physical reality. Imagine a universe where all the rarest phenomena occur simultaneously in one location. A strange quark star contains strange matter throughout its volume. Its core holds primordial black holes captured from the dark matter halo. Its magnetic field reaches magnetar strength. Its surface emits both matter and antimatter. This object would violate no physical laws. Each component remains possible individually, yet their combination approaches the limits of what nature permits. The probability of such an object existing anywhere in the observable universe shrinks to nearly nothing. Calculate that probability. Strange stars might represent 1 in every million neutron stars. Primordial black hole capture happens perhaps once in a billion years per star. Magnetar fields persist for only a few million years. Antimatter emission requires specific surface conditions. Multiply these probabilities together, and the result becomes infinitesimal. In our galaxy, containing 200 billion stars, perhaps a few dozen neutron stars exist. Among those, one might be a strange star. That strange star probably lacks captured black holes, magnetar strength fields, and antimatter emissions simultaneously. Expand the search to the observable universe. 2 trillion galaxies extend across 90 billion light-years. The total number of neutron stars exceeds our comprehension. Surely one bizarre combination must exist somewhere? Maybe. Statistics suggest extraordinary coincidences occur given sufficient opportunities, but observation remains impossible across such distances. The most distant galaxies appear as tiny smudges in the deepest telescope images. Individual stars are invisible. Exotic stellar remnants hide completely. We can observe only our local cosmic neighborhood in detail. Within a few thousand light-years, every star and remnant can theoretically be examined. This volume contains perhaps 10 million stars and a few thousand neutron star remnants. The sample size limits what rare combinations might appear. Yet even in this limited volume, astonishing objects have been found. Magnetars were discovered only in recent decades. Strange star candidates emerged from detailed observations. Ultra-high-energy cosmic rays revealed unknown acceleration mechanisms. Each discovery suggests rarer phenomena await detection. The ultimate rare object might exist in a regime we cannot yet access. Perhaps it requires quantum gravity to form. Perhaps it appears only during brief moments in cosmic history. Perhaps it produces signals we have not learned to recognize. Consider what the rarest natural object must involve. It would form through a chain of improbable events. Each step requires specific conditions met accidentally. The probability of the complete sequence becomes negligibly small. Yet somewhere in the universe's vast expanse, even negligible probabilities manifest as reality. Antimatter galaxies, if they exist, represent such ultimate rarities. The baryon asymmetry problem suggests matter vastly outnumbers antimatter. Any antimatter regions would be isolated and distant. Finding one would revolutionize cosmology and particle physics simultaneously. Or consider naturally occurring stable strangelets on Earth. Billions of years of cosmic ray bombardment might have delivered a few strangelets to our planet. They would sink toward the core and remain there indefinitely. Their total mass might be grams or kilograms distributed throughout Earth's interior. Detecting these embedded strangelets seems impossible with current technology. They interact only gravitationally at accessible energies. Their small size makes direct sampling hopeless. Yet they might be there, the rarest terrestrial material, invisible beneath our feet. Primordial black holes, smaller than atoms, drifting through the solar system represent another candidate. One might pass near Earth occasionally, detectable only through subtle gravitational effects on satellite orbits. The probability of close encounter remains tiny. Observing one requires extraordinary luck and precision. Each rare phenomenon connects to others through underlying physics. Antimatter teaches us about symmetry breaking. Astatine reveals nuclear instability limits. Strange quark matter probes the strong force under extreme conditions. Primordial black holes link gravity and quantum mechanics. Hawking radiation bridges thermodynamics and general relativity. Together, they form a tapestry showing nature operates at the edge of possibility. The universe does not merely permit interesting phenomena, it generates the most extreme versions compatible with physical law. Maximally dense neutron stars exist. Highest energy cosmic rays occur. Smallest possible black holes evaporate. This pattern suggests a principle. Whatever can happen, given enough time and space, does happen somewhere. The anthropic consideration extends to physical phenomena. We observe a universe rich in diverse structures because that is the only type that can be observed. If the universe were simpler, with fewer rare phenomena, intelligent observers might not develop. Complexity enables consciousness. Rare events seed galaxy formation, element production, and planetary systems. The ultimate rarity becomes not specific objects, but the existence of any observers to contemplate them. Yet we exist, we observe, we discover. Each rare phenomenon revealed enriches understanding and raises new questions. Why these particular physical laws? Why these specific constants? Why this level of complexity rather than more or less? These questions lack answers currently. They might lack answers forever. Or future physics might reveal deep reasons for the structure we observe. The search continues regardless. Every rare object studied brings us closer to comprehending nature's full scope. The rarest thing in the universe ultimately might be the universe itself. One cosmos among potentially infinite possibilities. This one, capable of producing observers, complexity, and extreme phenomena. We inhabit perhaps the rarest configuration of all. A reality that permits us to ask why anything exists at all. And in the end, the question remains open. What truly is the rarest thing? Antimatter? Astatine? Strange matter? Primordial black holes? Hawking radiation? Or consciousness itself, peering into the void, seeking understanding? The answer depends on your perspective. From a physicist's view, the rarest might be whatever combines maximum improbability with maximum significance. From a philosopher's view, perhaps existence itself claims the title. From your view right now, the answer might be the simple wonder that any of this is real. We have journeyed from laboratories trapping individual antihelium atoms to theoretical limits of physical law. We have explored stars made of quarks, black holes that evaporate, and particles that barely exist. We have seen that the universe operates not at median values but at extremes. These extremes define reality's boundaries. They show what is possible even if improbable. They demonstrate that nature is stranger than imagination. They prove that the rarest things, however unlikely, shape our cosmos in profound ways. The search for rarity continues. New instruments detect fainter signals. Better theories predict novel phenomena. Future discoveries might reveal rarities we cannot yet conceive. The journey has no end because the universe's capacity to surprise appears limitless. Perhaps that is the ultimate rarity, not any specific object, but the infinite creativity of physical law, the ability of simple principles to generate endless complexity, the emergence of structure from chaos, consciousness from matter, meaning from mechanism. In searching for the rarest things, we find ourselves. We discover that we too are cosmically improbable. The specific arrangement of atoms, reading these words right now, could easily have never existed. Yet here we are, contemplating the universe's strangest corners. That improbability makes every moment precious, every thought unique, every observation irreplaceable. The rarest thing might simply be now, this instant, this awareness that nature permits such wonder. Thank you for joining this exploration. The universe awaits further investigation. The rarest phenomena reveal themselves gradually to those patient and curious enough to look.